Pagi-pagi makan pelam, kayu tak sampai lempar selipa. Buka kata gunakan salam, supaya adab tak dilupa. Assalamualaikum warahmatullahi wabarakatuh. Salam, Om Swastiastu, Namo Buddhaya, Salam Kebajikan. Good morning and please be a part also. Ladies and gentlemen, welcome to the first International Conference on Chemistry Advanced 2024. Honorable Keynote Speaker, whom I deeply respect, Professor Perry Burham, MSc, Professor Dr. Yulfi Zetra, MSc, Dr. Rustam Tamim, Dr. Hasliza, Dr. Nurul Asikin Mijan, and Dr. Halim Salawat. Our respect to the Honorable Rector of Raja Ali Haji Maritim University, Professor Dr. Agung Damar Shakti, SPI DEA. Respected Vice Rector of Raja Ali Haji Maritim University, Dr. Tengku Said Razai, SPI MP, Dr. Nancy William, SSI MSI, Dr. Suryadi, SP MH, Honorable Head of the Bureau Academic, Planning, Enterprise and Collaboration, BA PKK, Ari Satya Dharma, SSOS MSI, Honorable Vice Director of the Graduate School, Dr. Ahmad Zahid, SPI MSI, Respected in attendance, Dr. Syed Fauzan Riyadi, SSOS IMAS, Dr. Doni Abdillah, MST, Dr. Mirna Sofia, MSI. Ahada Wahyusari, SPD MPD, Dr. Nefrita MPD MSI. Astama sponsor in attendant from Eco Green Oleochemicals Batam Company, Esko Bintan Indonesia Company, Wardah Cosmetic and Eduking Dear. Respect responsible of government institution present, Dinas Lingkungan Hidup, Dinas Energi Sumber Daya Mineral dan Badan Perencanaan Pembangunan, Penelitian dan Pembangunan Provinsi Kepulauan Riau, and all attended present in this room. Welcome to the Auditorium building of Raja Ali Haji Maritim University. Praise be to Allah Subhanahu wa Ta'ala, the Almighty God, for His grace and guidance. We can attend the event First International Conference on Chemistry Advanced 2024. I would like to thank for everyone attending our invitation. Ladies and gentlemen, please allow me Ziva Zain as the host today. Furthermore, let you sing the song Indonesia Raya and Mars Maritim Raja Ali Haji University. Ladies and gentlemen, please stand up. Thank you to all participants. Please sit up. Next is the traditional welcome dance from chemistry study program as the opening of the event. For the smooth running of this morning program, let's bow our head, raise our hand, and pray, which will be led by Eko Prasetyo. To Eko, the time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, the honorable guests. Before we starting this morning event, let us pray according to our respective religions and belief. I will lead the prayer in an Islamic way and for any religions also be adjusted. Al-Fatihah. A'udzubillahi minasyaitonirrajim. Bismillahirrahmanirrahim. Inna hamdalillah nahmadu wa nasta'inu wa nastaghfiru wa na'udzubillahi min syururi anfusina wa min sayyiati a'malina. Man yudillahu fala mudhillalah wa man yudillahu fala yahdilah. Asyhadu alla ilaha illallah wa asyhadu anna Muhammadar Rasulullah. Allahumma inna nas'aluka salamatan fid din wa afiatan fil jasad wa ziyadatan fi ilmi wa barakatan fi rizki wa taubatan qoblal maut wa rahmatan indal maut wa maghfiratan ba'dal maut. Allahumma hawin alaina fi sakaratil maut wa najata minan nar wa lafa indal hisab. Rabbana la tuzigh qulubana ba'da idh hadaytana wa hab lana min ladunka rahmah innaka antal wahhab. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azabannar. Subhana rabbika rabbil izzati amma yasifun. Wassalamun ala mursalin walhamdulillahi rabbil alamin. Assalamualaikum warahmatullahi wabarakatuh.
Thank you to Eko. To the next session, let us listen to Chairperson report by Putri Ramadhani. To Putri, the time is yours.
Pemandangan indah di kaki gunung, aliran sungai jernih dan tenang. Assalamualaikum saya ucapkan. Semoga acara ini sukses penuh harapan. Assalamualaikum warahmatullahi wabarakatuh. Shalom, Om Swastiastu, Namo Buddhaya, Salam Kebajikan Rahayu. Good morning and peace be upon us all. Honorable Keynote speakers, whom I deeply respect, Professor Peri Burhan, Dr. Rustam Tamim, Dr. Hasliza, Dr. Nurul Asikin Mijan, Dr. Halim Solawat, Respected Rector of Maritim Raja Ali Haji University, Profesor Agung Damar Sakti SPI DEA, Respected Vice Rectors of Maritim Raja Ali Haji University, Dr. Tengku Said Razai SPI MP, Dr. Nancy William SSI MSI, Dr. Suryadi SP MH, Honorable Head of the Bureau of Academic Planning, Entrepreneurship and Collaboration BAPKK, Ari Satya Dharma Esos MSI, Honorable Director of the Graduate School, Dr. Zahid, Respected Deans in Attendance, Dr. Said Fauzan Riyadi Esos, Dr. Doni Abdillah MSI, Dr. Mirna Sofia MSI, Warm Present Hari Wibowo MM. Estimated sponsor in attendance from Esko Bintan Indonesia Company, Eco Green Electrochemical Batam Company, and Wardah Cosmetic Company. Respected representative of government institution present, Dinas Lingkungan Hidup, Dinas Energi Sumber Daya Mineral, dan Badan Perencanaan Pembangunan, Penelitian dan Pengembangan Provinsi Kepulauan Riau, and all distinguished attendees present in this room. Dear conference participants, speakers, and invited guests, my fellow committee members who have worked hard, and all parties who have supported the implementation of this event. Alhamdulillah, we express our gratitude to the present to Allah Subhanahu wa Ta'ala, because with His grace and blessings, we can gather at this first international conference of the chemistry study program. It is an honor for us as the organizer to be able to welcome you all to this extraordinary scientific forum. This conference is held as a forum for sharing knowledge, discussing and introducing the latest innovations in the field of chemistry, but from the perspective of basic research, applied research, and technology development. We hope that this conference can strengthen international relations between academic, researchers, and practitioners in various fields of chemistry, as well as open up opportunities for wider collaboration. With the number of participants who took part in this activity, 51 presenters online, 16 presenters offline, 64 presenter posters, and 66 presenters recordings. We are very proud to be able to organize this conference for the first time, and hope that this event can be the first step of many international scientific activity to come. We would also like to express our deepest gratitude to all parties who have provided support, both materially and non-materially, so that this event can be carried out well. Sponsor of this ICCA activity are from UMRAH, EcoGreen, EduKing, ESCO, and Wardah. Hopefully this conference will provide great benefit for all of us, enrich our insights, and make a real contribution to development and science the technology in the field of chemistry. Finally, congratulations on participating in the conference. Hopefully this discussion and exchange of information that occur during this event can produce new ideas that are beneficial for the advancement of science and society. Dapat jemputan untuk kenduri, tapi telat kenelah lari. Saya haturkan 10 jari sebagai tanda pamit undur diri. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you to Putri. Ladies and gentlemen, move to the next session. Let us listen to the opening welcoming speech by Rector of Raja Ali Haji Maritim University, Profesor Dr. Agung Damar Shakti, SPI DEA. Please welcome.
Terbang merbah menuju muara, hinggap di dahan bunga mereka. Dengan bismillah awal bicara, sambutlah salam saya dengan meriah. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sejahtera bagi kita semua. Peace be upon you all. gentlemen, the Honorable Speaker, Keynote Speaker, Dr. Hasliza Bahruzi from University Brunei Darussalam, Professor Taufik Yap Yun Hin from University Putra Malaysia, Dr. Rustam Tamin from Kabul University, Afghanistan, Dr. Nur Asikin Mizan from University Kebangsaan Malaysia, Professor Ferry Burhan from Institut Teknologi 10 November Indonesia. Welcome to our campus, Pak. Dr. Halim Shalabad from Green Chemical Turkey, the Vice Rector, Dean, and also the lecturer from Raja Al Haji Maritime University, and of course the student from the Department of Chemistry, and also the student from Raja Al Haji Maritime University, and even from any other participant from other university. First of all, I would like to welcome you all with this international conference. I think this is the few international conference that held and conducted by our student, and we really appreciate and thanks for your big effort, especially for the chairperson that can manage this international conference with good manner, and I hope this international conference will successfully getting their objective in order to make the exchange, scientific exchange, the discussion among all the students and the academicians, and also the scientists representing by private sector, yeah. And thank you very much also for Eco Green, Oleh Chemical, Wardah, Cosmetic, and SCO that help us to help the student to co-organize and to co-funding this international conference. And the theme of this conference is very interesting, the green chemistry for a sustainable future. As we know that the growth of the development is always has the potential impact to our environment. If our environment has to be impacted, it's also the big question for the sustainability of our resources to support our living and welfare, livelihood and welfare. So this is very important for us to use or to optimize the technique and technology in order for our purposes with the good manner, with the wise manner. So the green chemistry is one of the solutions to mitigate the potential problem related with the sustainable development. Now, but I think during this international conference, the student can benefit to have some new insight and new perspective from the honorable guest speaker, and you can also discuss each other during the parallel session and try to find the best practice and try to find a new model, a new technique, a new technology that can help us to mitigate and to protect our environment in order for the sustainable development. But I have one challenge, because when we talk about the green chemistry, the problem is actually is still expensive to be implemented, so it's not affordable for everybody. One of the example is, for example, is and also there is some contradiction or some competition by promoting the green technology, for instance, the biofuel, but we have sometimes facing some problem, the competition with the food security. Yeah, when we want to create the biofuel using the any plant that can also be used for our food security is also some kind of that's something we will discuss today, and also we have to find the good solution for that. So that's why I think not only talking about the green chemistry, but also the potential I don't know this exists or not, the term, the blue chemistry, ya kan? So the blue chemistry, yeah, but of course it's also potentially related with the water environment, with the marine environment, with the ocean, because our university is the Maritime University, so our focus and our niche action should be related with the aquatic environment. So that's why green chemistry must be upgrading to become the blue chemistry. Yeah, for instance, when we talk about the producing biofuel, we can, of course, technically it's easy to culture the microalgae from the marine environment. And the microalgae needs to develop just two things. The first is they need the carbon dioxide, and the carbon dioxide can be pumping from the atmosphere or maybe from the release of the industry, so we can reduce the carbon dioxide extent in the environment, and to feed our microalgae in their bioreactor, and also they just need the sun energy, yeah, the photon from the sun energy. I think this is some kind that we have to promote, how to make the chemistry field is very important during our life, and to help us to develop and to fulfill our development with the sustainable manner. Yeah, I think you will get those information and those material of the presentation from all the speaker in this conference, and I hope you can enjoy this conference and getting the fruitful discussion during this day. So without further ado, I would like officially open this the first international conference of the chemistry advances, conducted by students from the chemistry department. I am very proud about that, because conducting the international conference with the output, the international publication in form of the proceeding indexes by the global index, such as the Scopus or Web of Science, is one of our key performance indicator for our university. So you are already give the contribution to the UMRAH portfolio. So it is a very important action, and I thanks to you all, the organizing committee, and all the supporting system, yeah, the lecturer, the dean, and of course also our partner from the private, yeah, to help us to realize this very important strategical international conference. Of course, because it's organized by the student, our student, the first, I mean, this is the first years of the student, yeah, yeah. So it's very impressive. I think what you have done is really, I know I cannot do like that. Yeah, I think what you have done is very, very huge action for our university. So again, I appreciate, and I'm sure that this is not this conference will be getting the success organization, and hopefully each year we can conduct this similar international conference with the other thematic and taken more broad participants from worldwide. Well, again, so officially I would like to open this international conference by saying Bismillahirrahmanirrahim. The international conference on chemistry advances I officially open. Bismillahirrahmanirrahim. Thank you very much for your attention. Another point for you is the Pulau Dompak nama diberi, tempat nelayan mencari tenggiri. Kalau kita kompak dengan green chemistry, pembangunan akan tetap lestari. Wabillahi taufiq walhidayah. Wassalamualaikum warahmatullahi wabarakatuh.
For Professor Dr. Agung Damar Sakti, please stay. And for Dr. Hasliza Bahruji and Dr. Rustam Tamim, please come forward for summation. And for Esko Bintan Indonesia. Professor Dr. Perry Burhan, please. For Prof. Perry, we thank you for warm opening and attention time as we officially open the first International Conference on Chemistry at Punch 2024. Next is a group photo session. Please stand up. Ladies and gentlemen, please stand up. Thank you, ladies and gentlemen. Please take your seat. I, Ziva Zain, as the host, handed over to the next program to moderator, Miss Rizdi Apsari Indah Pratiwi MM. Welcome together.
Honorable speakers, distinguished guests, esteemed participants, and all attendees of the first International Conference of Chemistry Advanced, good morning. It is my great honor to welcome you to this remarkable gathering of minds dedicated to advancing the field of chemistry. My name is Rizdi, and I am deeply honored to serve as your moderator for today's session. Together, we will explore groundbreaking ideas and cutting-edge innovations that hold the potential to shape the future of science, industry, and beyond. Now we are privileged to be joined by one of the most respected and influential figures in the field of chemistry, who will deliver the keynote address for today's session. Ladies and gentlemen, please join me in welcoming our esteemed keynote speaker, Professor Perry Burhan. Professor Perry, it is a great pleasure to have you with us today. Before we begin, allow me to take a moment to formally introduce you to our audience by sharing a brief overview of your impressive achievements. So, Professor Burhan is a highly esteemed scholar in the field of organic and geochemistry with over 3 decades of academic and research experience. Currently, he is a professor at the chemistry department of the 10 November Institute of Technology Indonesia. Professor Burhan holds a doctorate in organic geochemistry from Université Louis Pasteur, Strasbourg, France, where his groundbreaking research explored the origins and evolution of organic matter in sulfur deposits. His expertise spans organic geochemical analysis, sustainable fuel additives, and the application of advanced chemical methodologies in industry. He has also served in numerous leadership roles, including as the Director of Polytechnics, Energy and Mineral Akamigas, and the Dean of the Faculty of Mathematics and Natural Sciences at ITS Surabaya. His prolific contributions include editorial work for respected scientific journals and an impressive array of publications on energy, environmental sustainability, and chemistry. Today, Professor Burhan will share insights on empowerment of palm oil products towards green fuel, reflecting his commitment to advancing science and inspiring innovation. Professor Perry Burhan, the stage is yours. You have 30 minutes to share your thoughts. Thank you.
Ambil kayu untuk membuat meja. Kayu disatukan dengan paku. Sebelum presentasi ini dibuka, kuucapkan salam terlebih dahulu. Assalamualaikum warahmatullahi wabarakatuh. Good morning for all. I will present this cheerful morning our article entitled Empowerment of Palm Oil Products to Green Fuel. I am from Fuel Chemistry Laboratory in ITS Surabaya, and tomorrow morning, this morning, our presentation will begin with next week. Okay, with the introduction and then a mechanism of diesel lubricity bioadditive, and then class of bioadditive for lubrication fossil diesel, and conclusion. Okay. Let's start with introduction. Yeah. The demand for diesel fuel, you can see here, is predicted to continue to increase until years 2040. This is related to increase in diesel fuel consumption by land and sea-based vehicle. Combustion of diesel fuel with high sulfur content will produce SO2 gas. This SO2 gas contribute to acid rain. The activated catalyst in diesel engine exhaust system and corrosion of pipeline in oil refineries and harmful to human health. Sulfur in diesel fuel needs to reduce, ranging from 500 to 10 ppm. The Indonesian government, in particular, through the Directorate General Oil and Gas, has created regulation regarding the standard and quality of diesel fuel marketed domestically, starting from 500 until 50 ppm. One method to reduce sulfur in diesel oils is hydrodesulfurization, like this. Yeah. However, during desulfurization, with this method, the natural lubricating agent diesel is also lost. The loss of natural lubricating agent in diesel oil accelerate friction and wear in the diesel engine system. A further consequence in that the performance and lifetime in this problem to use additive based on vegetable oil. In the other hand, the growth of biodiesel production is driven by the escalation of energy needs and concern about environmental issues, increasingly emphasize the dependence on renewable energy source. Biodiesel is a renewable fuel, has refuel advantage over fossil diesel. These advantages include small gas emission, high flash point, availability of raw material, and easy to degrade naturally. Along with the growth of biodiesel production, there are major challenges that arise, especially related to management of byproducts and the quality of biodiesel itself. One of the biggest challenges is abundance of glycerol, which is a byproduct of biodiesel production. The surplus of glycerol causes an economic and environmental burdens. This surplus glycerol making it less economically feasible for biodiesel producer to manage and utilize it. Disposal of excess glycerol causes environmental problems because improper management can cause pollution of water bodies and soil. Now we will talk about bioadditive made from glycerol. First, mechanism of diesel lubricity of molecular level. Fossil diesel lubrication enhancer molecules have two main parts of their structure, a polar head and non-polar tail. We will show you how the lubrication mechanism of stearic acid. Stearic acid molecule move here randomly. The stearic acid randomly approach to iron atom in the surface ion oxide. This is from the engine. Oxygen atom of carbonyl and hydroxyl groups moves close to ion atom, and the alkyl chain organize themselves in parallel step for physical absorption and chemical absorption. As a result, the polar head of stearic acid, this one, is in the closest position to the iron oxide surface, while the non-polar tail is far from the metal film surface. The tails of the non-polar chain interact with each other through van der Waals force and support its toughness. Combining two absorption form protective layer to minimize direct contact between the metal surface and the different opinion on the whether of form a film is a single layer or a double layer in this one. This shows the orientation of the single layer stearic acid molecule shift when the metal to subjected to frictional and shear load. In contrast, shown the double layer arranged stearic acid in molecule. Psisorption occurs only on the iron oxide surface, while chemsorption involves the formation of a chemical bond between two oxygen atoms of the acid group and iron atom. The chemical bond can occur symmetrically and asymmetrically by sharing the valence electron of two oxygen atoms of the acid group with atom on the metal surface. Symmetric bonding occurs using the oxygen atom of the carbonyl groups and the hydroxyl group bound with different iron atom on the metal surface. In another symmetric form, two oxygen atoms of the acid group are bonded to the same iron atom on the metal surface. In asymmetric bonding, only the oxygen atom, the carbonyl group, is bonded in the iron atom. When rubbing motion is applied to the contacting surface, it causes the oxide to be removed. This condition can enhance chemisorption by formatting the bond of Fa carboxylate. In addition, the increase in local temperature to friction can also promote the formation of carboxylate. This phenomenon indicated that when sharing occurs, hydrogen tends to dissolve from the hydroxyl group to form carboxylate rather than maintaining the carboxylate bond. Next, please. We will talk about a bioadditive group for lubricating diesel fossil. First is ester. This ester synthesized from the three glyceride and methanol, and major product is methyl ester, like biodiesel, and then glycerols as byproducts. Fatty acid methyl ester produced has been known synthesizing from as a biodiesel, and researchers began to be interested in biodiesel as an alternative diesel fuel. Biodiesel also meet the requirement of green technology. That is, biodiesel can reduce friction, wear, and carbon emission. Biodiesel tribology behavior is caused by the consumption and structure of fatty acid content. The consumption of methyl ester of an unsaturated to total saturated effect the formance of tribology of biodiesel. However, our research state the effect of tribology biodiesel is caused by the structure of fatty acid. The methyl ester with hydroxylate fatty acid can increase the effect lubrication. For example, methyl ester with C80 and one hydroxyl group has better lubrication than C80 and without the hydroxyl group. The finding is accordance with report that the methyl ester chain strike on C80 has better lubrication than branch of methyl ester chain. Conversely, the methyl ester chain for C14 and C16 has better lubrication than the strike one. The degree unsaturated fatty acid chain can also increase the effect of biodiesel tribology. Unsaturated methyl ester is from fatty acid increase diesel lubrication better than methyl ester unsaturated fatty acid. Next, yeah. This the other is the nitrated ester. Synthesized from triglyceride or methyl ester compound as certain number enhancer and fossil diesel lubrication. As a model, oleic acid or methyl ester compound as certain number epoxidized, hydrolyzed, and nitrated. Lubricating testing of 0.01% nitrated ester compound shows the higher lubricating number than from the biodiesel. Next. Okay. I think we lost some page. Okay, next. Next. Oh, what? Okay. The next lubricating is malleated ester. Malleated ester was successfully modified from oleostearate methyl ester from tung oil. Oleostearate methyl ester was reacted with maleic anhydride and alkyl alcohol to form a compound with the structure like this. Yeah. This compound can reduce wear mark diameter WSD and friction by 40% and 47% when tested and as an additive for low sulfur biodiesel, low sulfur diesel. Next. The others is the triglyceride. Triglyceride have a good tribological performance because the polar and non-polar one that from the protective layer are separated. Triglyceride are potential candidate for fossil diesel bioadditive. The average WSD of low sulfur fossil diesel was 654 micrometer without any additive, with a film thickness of 2% and a friction coefficient of 0.383. However, after 1% castor oil was added to low sulfur diesel, the average WSD film thickness and friction coefficient became 100 96 micrometer, and 83% and 0.00676 respectively. Refined palm oil, RPO, also has good lubricating properties because it contains a rich palmitic acid or balanced amount of palmitic and oleic acid. However, triglycerides have some disadvantage, namely low oxidative stability and cold flow. Therefore, triglycerides can be modified to improve their chemical and tribological properties. Modification can be done by converting triglyceride into various lubricating enhancing bioadditive. The carbonyl compound in triglyceride act as an electrophilic agent, while the carbonyl oxygen act as nucleophile. If other species such as alcohol, acid, or base catalyst and certain reaction conditions are adjusted, the reaction will occur enough to carbonyl group to form various additives. Lubrication enhancing bioadditives are produced depending on the fatty acid in the triglyceride, the type of alcohol, and the molar ratio of triglyceride to alcohol. In this figure, we can show you how triglycerides are converted to various lubrication enhancing bioadditives chemically. From this triglyceride, we can amidation for fatty acid nanoamida, and then by trans-esterification, we can have ester and and hydroxylated ester. It's the best improver for lubricity. Okay. Next, what the molecular aspect? No, it's more. Yeah, fatty acid. Yeah, this fatty acid will different effect of lubricating with the long of normal alkaline. Yeah? More chain, longer the chain will be reduce the WSD value of the fossil diesel better. Next is the same in this from the without unsaturated, then one saturated and two saturated, or and one saturated and one hydroxyl group is more effect to reduce the WSD value on the fossil diesel. Next. The next we'll see the molecular aspects. First, the different fatty acid. Fatty acid is the normal alkyl. The more along the chain of alkyl, and this one about one the unsaturated, so the molecule will not linear, and then two unsaturated and three unsaturated, and with two more carbonyl groups. The second, unsaturated fatty acid are previously oxidized, and electrostatic force occurs between the molecules. This result is a good lubrication properties. However, when unsaturated fatty acids are oxidized, it impairs the lubricity of low sulfur diesel fuel and caused by peroxide compound that damage the lubricating film in the short term. While the positive impact occurs in the long term, it may be due to the polar molecules formed after oxidation, such as hydroxylated ester. These polar molecules are important to contributor to the improvement of unsaturated fatty acid lubrication. Next. Third, the partial hydrogenation. Partial hydrogenation from the unsaturated can apply to unsaturated fatty acid to examine whether the lubrication of unsaturated fatty acid is better or worse than the saturated fatty acid. Similar to methyl ester, after partial hydrogenation, the lubrication of monounsaturated fatty acid is better than that polyunsaturated fatty acid before partial hydrogenation. Next. Through molecular dynamic simulation, the diffusion rate of metal surface for unsaturated fatty acid is faster than that for saturated fatty acid. However, the lubrication behavior of unsaturated fatty acid is worse than for saturated fatty acid. This one, the head of lubricating agent, and this the ion from the engine. Next, yeah. I will show you how the synthesis alternative lubricating bioadditive for low sulfur diesel from castor oil. This one, our material is castor oil, and then we have the esterification, and the product, the component of lubricating is palmitate, stearate, oleate, linoleate, linolenate, and in castor oil is special compound is resinolelate oil. This one, F, no, this one, or this one. Yeah. Next, this the procedure of synthesis of two lubricating agent. One, the first we do the reflux, extraction, evaporation, products, and this the confirming the component of the triglyceride, and this one is the product of the lubricating agent. Next. This confirmation we use the GCMS. This one is the resinolate as the lubricating agent more better than the others. Next. This mechanism of formation, we start from ethylene glycol, and then with the triglyceride, and then we have the diglyceride. Diglyceride we can separate to monoglyceride, and we have the 2-hydroxyethyl ester. This one is the lubricating agent we use for diesel low sulfur. Next. This is the performance of our 2-HEE as lubricity improver for low sulfur diesel. Next. This pour improver low sulfur diesel 2. You can see the film thickness in 27%, and the after is 43%. This one, from the 62% to 56%, and the other. This one, I show you how to chemistry option between the two HEE before we adding the lubricating enhancer, and then the after lubricating agent added. Next. Okay. And then we can conclude our work to talking today. Is to time to migrate for us from fossil fuel to renewable fuel. And the second, we can use the diesel fuel, which is until mixture of biodiesel and petrodiesel still require additive to achieve the best performance of the raw material. One of the additive is the 2-hydroxyethyl ether, which can increase the lubricity effect value. Then the bioadditive raw material are plant material, so we can go to green chemistry. 2-HE has been synthesized successfully high-A resinolate, 2-HE linoleate, and 2-HE oleate. And then the performance of 2-HE demonstrated that it have potential a good lubricity improver bioadditive for low sulfur diesel. Thank you very much.
Thank you, Professor Burhan. Please give a warm applause. Thank you, Professor Perry Burhan, for your illuminating and inspiring keynote addresses. Your insights have shed light on the critical role of green chemistry in driving innovation and sustainability. Professor Perry Burhan, I forgot to ask your bonjour. All right, we now open Zubaybian. We now open the floor for questions for those who wish to engage with Professor Perry Burhan. Please raise your hand. Kindly state your name and affiliation before proceeding with your question. Any question? Or probably online participants? Oh, the chairman. Kindly state your name.
My name is Putri Ramadhani. Want to ask, my question is how sustainability approaches can be embedded in the palm oil value chain to produce environmental friendly green view. Thank you.
Thank you, Ms. Putri. Professor, do you get it? Oh, could you please, yeah.
How sustainability approaches can be embedded in the palm oil value chain to produce environmental friendly green view.
Professor, do you get it? Yeah, green fuel. Do you want to direct answer? Answer directly. Yes, please.
Okay, I will answer in bahasa Indonesia ya. Bagaimana kita menggunakan minyak sawit untuk menjadi bahan bakar yang green chemistry. Begini, jadi saya sebenarnya lebih mendalami banyak fossil fuel, khususnya di upstream, di hulu. Tetapi sekarang tuntutannya adalah kita harus berkembang ke ke hilir. Jadi yang tidak lagi menggunakan fosil, tetapi menggunakan bahan bakar yang dapat dibuat ulang, ya, jadi dapat diperbaharui. Nah, minyak palem atau minyak sawit itu kita rubah menjadi esternya, maka ester ini akan menyerupai bahan bakar fosil untuk tingkat solar atau diesel. Ada kelemahan, ada kelebihan memang. Ya, kalau pada fosil diesel, dia mempunyai apa yang disebut dengan daya lumas. Ya. Jadi dan itu disebabkan oleh belerang yang ada ya atau merupakan kandungan dari fosil diesel. Tetapi belerang ini kalau dibakar itu mengeluarkan SO2, itu tidak ramah lingkungan. Nah, itulah yang menguntungkan bagi diesel fuel. Jadi minyak palem dijadikan diesel, dia tidak punya belerang untuk melubricate, melumas mesin. Sebagai upaya untuk memperbaiki rendahnya lubricity properties dari minyak palem ini, minyak sawit ini, biodiesel ini, maka dibuatlah aditif. Nah, kita sekarang ini sedang mengembangkan berbagai aditif dari sisa pembuatan minyak atau diesel atau biodiesel.
Miss Putri.
Okay, thank you.
Thank you.
You understand your answer.
Yeah, Miss Putri. I want to open another question. Any question? Oh yes, please. Wow. Oh, all right. Oh, hi, Professor.
I'm just a layman. Yes. Salam kenal, Prof. Ferry. I'm a layman in chemistry, in whatsoever. I don't have any chemistry with anybody. Yeah, the question is about, is diesel fuel is used for lubrication? Is it a fuel or a lubricant? Thank you.
Professor Indra.
Yeah.
We are sorry,
Yes.
but your voice is not clear.
Okay.
Atau
What
mungkin,
should I say?
atau mungkin boleh pakai bahasa Indonesia aja, Prof. Indra.
Itu minyak diesel, bahan bakar diesel, itu dipakai untuk lubrikasi atau untuk pembakaran?
Kami saat ini mengembangkan untuk bahan bakar aditif untuk bahan bakar diesel. Jadi sebagai aditifnya. Jadi bukan sebagai lubrikan, tetapi diesel itu memerlukan
diesel sebagai bahan bakar.
betul,
Memerlukan lubrikasi.
memerlukan agen lubrikasi ya.
Kenapa minyak bakar, bahan bakar yang dari fosil fuel itu nggak perlu
Ya,
lubrikan?
karena dia mengandung belerang. Jadi kandungan belerang dari fosil diesel itu sudah memberikan sifat lubrikasi. Tetapi sebagai konsekuensinya, maka fosil diesel ini dalam pembakaran akan mengeluarkan SO2. Gitu. Nah, sekarang juga fosil diesel itu kan kandungan belerangnya diusahakan sesedikit mungkin. Nah, akibatnya sifat lubrikasinya juga menurun. Nah, sekarang juga ditambahi dengan aditif untuk mengembalikan sifat lubrikasi tersebut.
Jadi di hari ke depan nanti itu mesin diesel nggak pakai pelumas di bawah, di oil sump-nya, ada tempat ada minyak pelumasnya, itu bakal nggak ada tuh, karena bahan bakarnya sekalian pelumas.
Bukan, Mbak. Jadi ini dua hal yang berbeda. Kalau pelumas kan untuk di mesinnya. Nah, yang ini di bahan bakarnya. Nah, bahan bakarnya itu sendiri di dalam, menurut saya kan orang kimia, Pak. Jadi yang menurut orang mesin itu harus mempunyai sifat lubrikasi. Sebab kalau tidak, seperti yang saya gambarkan tadi, ada lapisan Fe dari mesin itu dapat tergores oleh pergesekan mesin, begitu.
Oke, terima kasih banyak, Prof.
Ya, terima kasih.
Thank you, Professor Indra. It's nice to meet you. All right.
Yes. Thank you.
Any other question? Oh yes, the beautiful lady.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
My name is Farol Fahrezi from Program Study Chemistry. I have one question for you, Prof. My question is, how can the latest technologies enhance the efficiency and sustainability of biofuel production from palm oil? Maksudnya, bagaimana teknologi terkini dapat meningkatkan efisiensi dan keberlanjutan produksi biofuel dari minyak sawit? Thank you, sir.
Thank you, Miss. Sorry.
Ya,
Miss
yang
Farol.
ditanya teknologi mesinnya atau teknologi bahan bakarnya?
Bahan bakarnya, Pak.
Nah, ya, kalau teknologi bahan bakarnya antara lain itu adalah dengan meningkatkan daya lubricity-nya. Tetapi sebenarnya tidak hanya itu, ya. Jadi ada yang harus ditingkatkan itu adalah sifat lubricity, kemudian juga harus dijaga. Mungkin untuk Indonesia nggak ada masalah. Apabila mesin itu misalnya mobil berjalan di negara yang bermusim dingin, maka diesel itu dapat dapat lebih mengental. Nah, itu menyulitkan mesin untuk bergerak, bahkan bisa mesin itu berhenti. Nah, oleh sebab itu harus ada agent untuk low cost. Jadi untuk membuat diesel itu dapat mengalir dengan mudah. Nah, itulah yang diperbaiki dari sifat-sifat diesel fuel, dari fuel diesel. Begitu.
Oke, thank you, Prof.
Any other question? I feel like it's getting interesting, the discussion. Yes. Please kindly state your name.
Assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself. My name is Marcella Audiatati from a chemistry study program. I want to ask, what is the role of palm oil in the green energy transition? Maksudnya, apa peran minyak sawit dalam transisi energi ramah lingkungan? Thank you.
Thank you.
Baik, apa peranan minyak sawit dalam menghasilkan fuel? Transisi energi ramah lingkungan. Jadi yang pertama kita dapat menggantikan bahan bakar yang fosil yang di negara kita ini sudah mulai berkurang jumlahnya, ya. Jadi kita dapat gantikan dengan minyak palem itu. Nah, kemudian terhadap lingkungan, beberapa sifat dari biodiesel itu mudah kalau ada buangannya terhadap lingkungan itu mudah dihancurkan, mudah didegradasi. Jadi bekasnya itu tidak merusak seperti fosil diesel. Ya. Nah, transisi energi, saya kira saya bukan ahli energi, ya, tetapi ya, ahli dalam bahan bakarnya. Bagaimana kita menjadikan yang tadinya minyak palem atau minyak sawit yang menjadi konsumsi manusia sekarang dijadikan konsumsi mesin. Nah, ini walaupun jadi problem bagi negara kita terhadap Eropa, tapi kita punya cukup banyak minyak sawit yang dapat kita rubah menjadi bahan bakar.
Thank you, Professor Perry.
Okay, thank you for the answer.
All right. Do you still want to? We still open the question, probably from Mr. Oh, ramai sekali ini ya.
Assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself. My name is Handa Sadewa Prasetya. I'm from the UMRAH Chemistry Study Program. I'd like to ask what policy measures are needed to support the empowerment of palm oil products as green fuel. Artinya, maksudnya apa langkah-langkah kebijakan yang diperlukan untuk mendukung pemberdayaan produk minyak sawit sebagai bahan bakar hijau, Pak?
Oke, kalau kebijakan nanti kita urusan pemerintah gitu ya. Tetapi paling tidak sekarang kan sudah ada banyak aturan-aturan yang terkait dengan mendukung itu disusun oleh pemerintah. Bagi kita terutama bagi orang kimia, sekarang bagaimana kita mencoba memanfaatkan minyak sawit itu menjadi bahan bakar yang ramah lingkungan. Yang pasti minyak sawit ini jauh lebih ramah lingkungan daripada fosil. Jadi dengan kita menggunakan minyak sawit itu sendiri berarti sudah kita mengarah kepada yang green lingkungan. Yang green, ya. Oke, mungkin cukup banyak. Satu lagi mungkin pesan dari saya gitu, karena saya juga berkecimpung di bahan bakar baik yang dari hulu, terutama di hulu, kemudian karena ini mengikuti kebutuhan negara kita karena minyak bumi itu sudah semakin habis, ya. Jadi minyak bumi Indonesia itu seharusnya kita bisa produksi dalam sehari itu 1000 barrel, ya. Tetapi kenyataannya sekarang dalam beberapa tahun terakhir ini Indonesia hanya mampu untuk memproduksi minyak sekitar 600-700 barrel saja per hari. Artinya kenapa itu terjadi? Karena cadangannya sudah semakin berkurang. Nah, oleh sebab itu tentunya kita perlu untuk berpindah ke yang dapat diperbarui. Salah satunya kalau kita menggunakan bahan bakar adalah yang berasal dari minyak sawit, tetapi tidak minyak sawit saja, ya banyak. Nah, dari minyak sawit itu juga banyak hal yang dapat kita turunkan produk-produknya. Antara lain kami menspesialisasi untuk aditifnya. Jadi selain, karena begini, saat ini kan biosolar itu baru sampai 35, B35, artinya solar dari minyak dieselnya, dari sawit itu 35% dan fosilnya masih 65%. Nah, ini tentunya masih perlu dibalansi untuk lebih banyak lagi. Nah, oleh sebab itu kita perlu aditif untuk menyempurnakan biosolar tersebut. Nah, bagi ibu bapak atau adik-adik sekalian, kalau ada yang berminat mempelajari lebih dalam, kami undang ke ICCA untuk program S2 atau S3. Silakan.
It's a privileged invitation from Professor Perry. Thank you, Professor. Masih ingin cukup? Cukup? Oke. Nampaknya masih ada beberapa pertanyaan tadi ya. Nanti ya bisa disampaikan di luar, disampaikan ke panitia atau di email ke Profesor ya. Alright, as we close the session, I would like to express our heartfelt gratitude to Professor Perry Burhan for his thought-provoking presentations and for sharing his invaluable knowledge with us. Your contribution to green chemistry are truly inspiring and align perfectly with the theme of this conference. Thank you, Professor Perry Burhan. Professor, we would like to thank you, and there ada cenderamata. Oh ya, Profesor Perry Burhan, ada cenderamata yang ingin diberikan oleh Ibu Dr. Nancy, silakan Ibu. All right. Ladies and gentlemen, are you still with me? Are you still focused on this conference? If you're still focused, I want you to raise your right hand. Yeah, right hand, left hand. Okay, all right. Now we move to the second speaker. Ladies and gentlemen, please join me in welcoming our esteemed keynote speaker, Dr. Rustam Tamim. Dr. Rustam Tamim, let me introduce you for a brief. Chituri. Hailing from Afghanistan, Mr. Tamim has an impressive academic background and extensive experience in the fields of chemistry and material sciences. He holds a master's degree from the 10 November Institute of Technology ITS in Indonesia, where he contributed significantly to research on advanced materials and sustainable technologies. Mr. Tamim has participated in numerous international workshops and conferences, sharing his insights on topics ranging from molecular magnetism to renewable energy solutions. His published works featured in prominent journals include Innovations in Biojet Fuel Production and the Synthesis of Sustainable Materials. Today, Mr. Tamim will be representing on low temperature pyrolysis of waste cooking oil using marble waste for biojet fuel production. Mr. Rustam Tamim, stage is yours. You have 30 minutes.
Thank you very much. Ya, selamat pagi semuanya. Masih semangat ya? Is it on? Selamat pagi semuanya. Good morning everyone. Selamat pagi. Masih semangat ya semuanya? Huh? Okay. Today we will discuss about a topic which is low temperature pyrolysis of waste cooking oil using marble waste as a catalyst for biojet fuel production. We will discuss about the keywords, introduction, experiment part, as well as the conclusion. In the keywords in highlights, we will discuss about marble waste, what is marble waste, what is the composition of the marble waste, and also we will talk about the waste cooking oil and deoxygenation, which is pyrolysis, as well as biofuel, biojet fuel, and catalyst characterization, which is fresh catalyst characterization, as well as used catalyst characterization, and also the product analysis, the liquid product analysis, and characterization. Yeah, you just bring the full slide. The full slide. Full slide. Okay. All we knows the words needs energy. Everything, everybody needs energy. Start from a very small equipment, very small material, handphone, till satellite, till everything needs energy. We needs energy. Human needs energy. So, as a researcher, beside we produce the energy, we find the way to produce the energy. There is a lot of challenges with that energy. Maybe the challenge we can say about the climate change, about the air pollution, about the water pollution, as well as the solid waste. So all these demands from the energy production we keep in mind, and we are finding, we are looking, we are searching for alternative way to produce energy, meanwhile to be environmental friendly situation. So as we can see the report of the International Energy Agency till 2025, till 2025 here, the energy production source is from the oil, which can cause for a lot of damage in the environment. Since that, we can see till 2050 the report got changed. The energy source which produce the energy from oil goes to the renewable energy. Because why change the plan? Because the renewable energy decrease the challenges of the environment. So since that, go ahead. Since that we are looking for a source that will be environmental friendly to produce the energy, and we are looking for a renewable energy. In this slide, you can see some types of renewable energy just for the knowledge, a lot of types of the renewable energy, and also the source for the biomass, you can see in the slide. And then go next slide. There is also some example of these energy production sources or feedstocks from the non-edible and edible oil, and then from there we get next slide. From there we understand, and we took the waste cooking oil as a feedstock for this biofuel or fuel production as a source, energy source. Okay. multiple reasons are there. For example, why we choose waste cooking oil? Because it is cycling environment, economical cycling. Okay, so we are cooking and we are generating the waste cooking oil. From there we take again, we use it for the energy, and again this is economical recycle. And apart from that, there is a lot of application beside the that. A lot of application can be used for the polymer, can be used for other many application you can see here. And this is the environmental aspect. From the chemical aspect, we see the waste cooking oil contains a lot of fatty acids, which can be converted to the fuel or to the biofuel by cracking using a catalyst. That is why we choose a waste cooking oil. Next one. Okay. What actually happened, how we started, we took marble waste as a catalyst. Marble waste we took from the Tulungagung, which is in Surabaya, not Surabaya, Tulungagung, east of the Java. And then the marble waste, we took it and we sieve. We mix slurry or powder. And then from the characterization, the composition of the marble waste, we see as calcite, dolomite, and quartz. That is from the XRD characterization. And from there we understand we can use this material as a catalyst for the deoxygenation or pyrolysis reaction. And beside that, we took the waste cooking oil, which is the main compound triglyceride, and we filter, we washed, and then using deoxygenation reaction, cracking by the marble waste, which is base catalyst, in inert condition, in a very low temperature around 380, and we got the compound. This compound has been analyzed, characterized by the GCMS, and we see it is content of the biojet fuel and also fuel. Okay. The optimization of the reaction condition can be catalyst, catalyst dosage, many different concentration, also the temperature, the reaction time, and reusability. And also we can see the marble waste application, it has a huge application, specifically for the biojet fuel production, and also the rubber polymer can be used as a filler in polymer, in rubber polymer. So it has a huge field of application. Go next. Yeah, click. Okay, here is the optimization condition of the reaction. Okay, we use multiple dosage of the catalyst, which is, multiple temperature, 380, 360, and 400. And the result shows the maximum yield result is in 380, which is the optimization procedure. Okay, next. And also for the optimization, we collect the compound, the liquid yield, in different hours, for like first hour, second hour, third, fourth hour. And also the dosage of the catalyst, which is different percentage. And we saw the result, as much as the percentage of the catalyst increase, the yield get decreased. But it doesn't mean that compound is a good quality compound. So only to see the yield, it is in that order. But in quality base, the order get changed. Later we'll see. Next one. Okay. We characterize the catalyst to see what is the composition and is it suitable to be as a catalyst? Yeah, of course. You see XR depicted here. It contains related to the the dominant peak is related to the calcite, which is calcium carbonate, and the second one is related to the marble dolomite, and this one is related to the quartz. And also the use catalyst, the XRD of the use catalyst shows similar peaks are there, but not in that concentration. So it means there is still those compounds there in the catalyst, but not in that high percentage, but still we can use it as a catalyst. And also the broad peak shows the amorph form of the used catalyst. Okay, here I want to show after the reaction which we burn this waste cooking oil along with the marble waste. So we got burn marble waste as well as waste cooking oil. So here is these two peaks can get increased if we compare to the fresh catalyst, which related to the carboxylic acid CH form base of this. So it means the carboxylic acid get back to the compound after this burn the result. Go ahead. Okay. Also for the pore size and also the surface, we characterize the catalyst using the nitrogen absorption analysis, and it shows the pore size is 3.7, almost 4. It's like nano compounds, nanocrystalline material. As we know, for the fuel production or biofuel production, the better catalyst may be mesoporous, but still the marble waste, as it is cheaper, so as still we can use it as a catalyst. Go. Okay. For the thermal analysis to see in how much temperature this catalyst get decreased or decompose, we can see in 600 to 700 around it get decomposed. And for the used catalyst, which is very interesting, there are 3 different phases which shows the soft coke, the hard coke, and also the carbonate in different temperature, it get decomposed. So, but still there is carbonate and also there is a carbon char. So the carbon char gets decomposed in a low temperature, and the carbon is still similar with the fresh catalyst. Go ahead. Okay. For the morphology, to compare the fresh catalyst as well as to the used catalyst, same morphology shows ununiform nanocrystalline material. In the EDX analysis show the maximum compound there is calcium carbonate, which is calcium around 25%. But if we see the used catalyst, the dominant compound there is carbon, the element is carbon, which is getting to 48%. But the morphology is similar, but it's getting little bit change from the fresh catalyst. Go ahead. Okay, it's the same catalyst characterization, and you showing the morphology of the catalyst. Go. Okay. As I said, it is a base catalyst. Marble waste has calcite, dolomite, and quartz. It means it is a base catalyst. To know the basicity of the marble waste, we run TPR and TPD of the marble waste. And here you can see very sharp peak in TPR and also in TPD. It shows it is a very good base catalyst. But beside that, there is also other peaks which is related to like weak, medium, and strong base side. Right? And this is for the potential for the binding energy. We use the XPS to know all the elements which is there in the marble waste show their own binding energy in a different electron potential. Go ahead. Okay. Start with the liquid analysis. We got the liquid, we got the product, we analyze the product using different formulas, selectivity, liquid, and all these things. We using these all formulas. You can see the paper maybe in more detail there. Okay. To see the reaction, the pyrolysis take place or not, we record the FDIR of the liquid product of the waste cooking oil, which is starting material, compared to the product. But the product collected in different hours, like first hour, second hour, third hour, fourth hour. But overall, if we see these two peaks, which is related to the carboxylic acid, okay? Starting material, there is a very sharp, those two peaks. It means there is a high percentage of the carboxylic acid. But if you compare it to the product, these two peaks getting decrease or disappear. If we see in the last hour production, is disappear, but in the first hour still there is a very low concentration. So it means the reaction, the pyrolysis reaction, take place and it is converting to the product. Go ahead. Okay. Conversion on and the selectivity of the product we see here, as I said, as long as the catalyst percentage is increasing, the yield, the conversion get decreased, but it doesn't mean that is a good product, high quality product. Okay. As well as the selectivity of the gas, char, and the liquid, here you can see. And this is the products, very clean, green products, environmental friendly. From the color you can see E1. Okay, go ahead. Okay, as I said, for the optimization, we record the temperature in 380 and collecting compound in different hours. You can see here the dominant one is compound collected in the first hour, second hour, third hour, fourth hour, very less. So it means if you run the reaction even for 1 hour, it is enough. You will get 70 or 75% the product. So it doesn't take long time. It is time limited compound reaction, and as well as the yield. In the GC-MS analysis of the product based on the functional group, the product says where there is 0% of the catalyst, no catalyst, the carboxylic acid percentage is very high. It is around 40% plus, 40+%. But along with the other linear and cyclic compound. But when we start using the catalyst, the carboxylic acid percentage is getting decreased from 45% to almost 3 or 4%. So it means the catalyst is doing its work, and it is producing a high quality biofuel compound. Go. Okay. To see, is it that catalyst recyclable? Can we reuse the catalyst? We record 3 times recycle reaction, the reaction for the compound. But the first cycle you can see still the carboxylic acid amount is less. In the other amount you see the linear and also the cyclic amount is more. But when it goes to the second cycle or to the third cycle, the acid percentage is getting increased again. It means the quality is getting not that good quality biofuel, but still it is okay. It is still okay. Still we can call it the biofuel, biojet fuel. In also the conversion, we can see the conversion is start getting decreased from the second to from the first to second, and from the second to third cycle. Okay, go ahead. It has to be in the beginning, but let's discuss it here. Why we call our compound biojet fuel? Okay, we did some literature review. This is previous research. when there is carbon chain compound from C8 to C16, they call it biojet fuel. Whatever it is, cyclic or it is linear compound. And these are the literature review. I took it from the publication. In the maximum, it is 64%. In our work, we got that range compound, C18 to C16 compound, when we are using 9% marble waste to 70, almost 71%. It means we get the biojet fuel compound. Okay, go ahead. Okay, as a conclusion, I can say this material, we can use it as a catalyst for biojet fuel production. And it has the capacity to decrease the carboxylic acid amount from 49% to 4%. And we finding shows that the untreated marble waste containing calcite, dolomite, and quartz increase the selectivity of hydrocarbon in low temperature pyrolysis. It means we can use this catalyst for the biofuel production in low temperature. In 380 or 360, we can use it. So it is temperature, low temperature, it is time limited, you can save the time and you can get the compound compared to the previous study. Next one? No next? Okay. Thank you very much. That was from my side. Yeah.
Thank you, Dr. Rustam Tamim, for your illuminating and inspiring keynote address. Please have a seat with me. We now open the floor for questions. For those who want to engage with Dr. Rustam Tamim, please raise your hand. Kindly state your name and affiliation. Any question? In Bahasa is okay. Do you speak Bahasa Indonesia well? Do you still speak Persian language? Persian, Chituri. Tasyakur. Any question? Online participants? Oh, we have Professor Indra Putra Alamanar once again. Seems like you. Hi, Professor.
Thank you.
Do you have any question for Dr. Rustam Tamim?
Oh, yes. Thank you. Yes, the question is, what ethics should we follow when using catalysts which are mostly made from materials that is not environmentally friendly to produce environmentally friendly products? A contradiction in this case. What should we do? Thank you.
Do you understand the question? No. Professor Indra, probably you can state in Bahasa.
Oh,
Yeah.
okay. Ethics apa yang harus kita ikutin atau kita anut kalau kita pakai katalis yang kebanyakan tuh dari bahan-bahan yang tidak environmentally friendly untuk bikin barang-barang yang ceritanya environmentally friendly. Begitu, jelas.
What asset should we use? If I'm not mistaken.
Yeah. What ethics? Ethics. Etika.
Oh, ethics. What ethics?
That we should follow. Apa etika yang harus kita anut?
Oh, what ethics should we follow
When using catalysts
when using catalysts
which are mostly made from materials that's not environmentally friendly,
regarding the material that is not environmental friendly, the
to
ethics.
produce environmentally friendly products.
Yeah, the ethics.
Okay, sir. Thank you. So, which ethics we have to use the catalyst which is not environmentally friendly?
Mostly because it's from rare materials, from very difficult to find materials. We use it as catalyst.
Mm-hmm. Yeah, actually, we are trying to use, there is like different aspects and different factors. We focus on that in a catalyst to produce environmental friendly, okay, to produce that. So in my work, like this biojet fuel production or biofuel production, focusing on the reaction condition, which is also the composition of the compound and as well as the condition of the reaction. So we reduce the compound from the acid to low acid or from the zero acid. So it will be environmental friendly, okay? But mostly the previous work, the catalyst they have used is like, if there is zinc, if there is some not environmental friendly element in the catalyst, which is not good for the environment, we avoid that. We avoid that. So in this catalyst, the main compound is calcite, which is calcium oxide, calcium carbonate, and we go to calcium oxide from the like zinc oxide or some other oxide, some other element. So yeah, that is the main point we focus here for that.
Yes, because the interest here is if you can produce a catalyst from the environmentally friendly materials, you can produce a hell lot of environmentally friendly products.
Yes.
And why there is no research on that?
Why it is?
Why there is no research on the environmentally friendly catalyst?
Okay, there may be some research, but it depends on the percentage. Like, it's not environmental friendly 10%, 20%, or how. So it depends on the, and still we are looking for the alternative way to make a catalyst which is can produce like 0% environmental environmental not friendly compound. Yeah.
Okay, thank you.
Yeah, thank you, sir.
Thank you, Professor Indra. We still open the floor for questions in this room. Any other question? From Mr. Hilfi, probably. Dr. Nancy, probably. Oh, yeah.
Hello everyone, my name is Harabi. I'm from a study program of chemistry. So my question is, what are the main challenge in integrating biofuels as a sustainable and commercial fuel source? Dalam bahasa Indonesianya, apa tantangan utama dalam mengintegrasikan biofuel sebagai bahan bakar berkelanjutan dan komersial?
Thank you, Mr. Harabi, if I'm not mistaken. So, do you understand the question? The main challenge to mitigating the
main challenge of the fuel to the environment. Yeah. As I said in the presentation, so challenge of fuel to the environment is to make the pollution, okay? Because it produces mostly carbon dioxide. And uh, we are trying as a researcher, we are trying to find the fuel. That's why we call it biofuel or green fuel or biojet fuel or this thing, to produce a compound which can produce less amount of carbon dioxide or zero. Yeah, zero for that. And it all comes from the acid which contained there in the liquid. So we are trying to produce less percentage of the acid compound fuel, acid fuel, or maybe zero acid fuel. Yeah.
Okay, thank you very much, Professor.
Thank you. Any other question? Oh, yes.
Assalamualaikum warahmatullahi wabarakatuh. My name is Sanda Sadaya Prasetya. I want to ask how do the efficiency and environmental impact of biofuels derive from organic waste compared to fossil fuels and other renewable energy source? Maksudnya bagaimana efisiensi dan dampak lingkungan dari biofuel berbasis limbah organik dibandingkan dengan bahan bakar fosil dan sumber energi terbarukan lainnya?
What is the efficiency? Huh? What is the efficiency?
Yes, and environmental impact.
Yeah, environmental impact. Yeah. As I said there in the, I think in the second slide, so a lot of environmental impact is there, like waste, like every waste, char and the solid waste, the liquid waste, because as a human, we don't care about our environment, about the environmental impact. And even though it is not good for human, it's not good for the other animals, but we don't care. So, but the focus or the efficiency will be like to try to find alternative way to produce environmental friendly energy. Okay, maybe like electric car, or as a this research to get very clear, very good quality biofuel to be environmental friendly for all of us. Yeah, so we focus using alternative way, even in the chemical, that we don't should use the chemical that is not environmental friendly. Like I said, zinc is killing small animals, so the microorganism. So even it's not good. So we have to be looking for environmental friendly chemical, the procedure, the way, as well as the product. All these aspects can be a good efficiency for the environment.
Thank you very much, sir.
All right. Do you still want to open the question? All right. I think it's enough for this session. If you have any question, please note to the committee or email or send email to Dr. Rustam Tamim. All right, as we close this session, I would like to express our heartfelt gratitude to Dr. Rustam Tamim for his inspiring, invaluable knowledge with us. Your contributions are truly inspiring. Thank you, Dr. Rustam Tamim. Please give a round of applause. kepada Bu Nina dimohon untuk memberikan cenderamata kepada Mr. Rustam Tamim. Thank you, Dr. Nancy. Kami mohon kesediaannya untuk maju ke depan, Profesor Peri Burhan, kemudian perwakilan dari ESCO, para sponsor, mohon maju ke depan untuk kita dapat melakukan foto bersama. Pak Hilvi, silakan. Thank you once again, Dr. Rustam Tamim and Professor Peri Burhan. Ladies and gentlemen, as we come to the end of the session, I want to take a moment to express my deepest gratitude to our speakers, Professor Peri Burhan and Dr. Rustam Tamim, for their insightful presentation and for sharing their expertise with us today. The knowledge and perspectives they have provided are truly invaluable. I also want to thank you, all of you, for your active participations, thought-provoking questions, and engagement throughout the session. Your enthusiasm adds so much value to the discussion. Let us take the ideas and learnings from the session forward, applying them in our respective fields and in continuing the conversation beyond this room. Once again, thank you for your time and attention. We look forward to seeing you in the upcoming sessions and wish you a productive and inspiring remainder of the conference. Thank you and have a wonderful day.
yang sulit. Pasti itu ada. Itu saja paling wajib. Fokuskan. Semua model termasuk ini.
Halo? Ya, ada yang bisa dibantu? Oh, Ibu. Baik. Can we begin committee? Bisa dimulai? Okay, first thing first, maybe I would like to say hello to our keynote speaker for the next sessions, Ibu Nurul and Ibu Azriza.
No.
Okay, am I audible? Can you hear me clearly?
Yes, I can hear you clearly.
All right, can we begin the next sessions? Yeah, I think so. Okay, Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Honorable to the Dean of Faculty Engineering and Marine Technology of Universitas Maritim Raja Ali Haji. Honorable Coordinator of Chemistry Study Program Universitas Maritim Raja Ali Haji. And I also would like to honor our keynote speakers from Universitas Kebangsaan Malaysia, Dr. Nurul Asikin Mijan, and from University Brunei Darussalam, Dr. Hasliza Bahruji. Hello, Dr. Hasliza. Are you here with us?
Hello.
Yeah,
Yes, I am with
okay.
you.
Yeah, okay. And honorable, all of the distinguished guests that I cannot mention one by one. Then the last but not least, honorable all participants in this conference. Yeah, welcome to this session, ladies and gentlemen. Firstly, I would like to welcome you all in the first international conference on chemistry advance, or ICCA. And in these sessions, I'm Hanifa. It gives me a great pleasure to be the moderator for the second keynote speaker sessions. And in these sessions, we have 2 online keynote speakers. So make sure all of you follow this session till the end. Okay, without any further ado, let's say hello to our keynote speakers in these sessions. The first keynote speaker is Dr. Nurul Asikin Mijan from Malaysia. I bet that Dr. Nurul already here. And let's kick off the session, Dr. Nurul. So Dr. Nurul. Hello.
I think first session will be Dr. Hasliza, isn't it?
Oh, it should be Dr. Hasliza?
Yeah.
Oh, okay. All right. My bad. All right. Hasliza, let's begin these sessions. So you're gonna have 25 minutes to present your presentations, and after that we're gonna have Q&A sessions. And after your turn, we will come to Dr. Nurul. All right, Dr. Hasliza, you may share your screen, or the committee will help you to show your PPT. Which one? Do we have the presentation slide? Okay, maybe Doctor, you can share your screen if it is possible.
Wait.
Okay. While waiting, let me
introduce you to the audiences in this room and also to online audiences in this Zoom meeting. I will read your short biography first. Okay, ladies and gentlemen, our first speaker is Dr. Liza Bahruji from University Brunei Darussalam. Hello, yeah, from University Brunei Darussalam. Then Dr. Hasliza is senior assistant professor at Center of Advanced Material and Energy Science. Then her last education is in Cardiff University, UK. And Dr. Hasliza already achieved a lot of reward and published many research that I cannot mention one by one. And the research areas or teaching areas and interests of Dr. Hasliza is general chemistry, inorganic chemistry, heterogeneous catalyst for renewable energy, nanotech application for food industry. And if you want to meet Dr. Hasliza in person, we can come to Central of Advanced Material and Energy Science in University of Brunei Darussalam. Yeah, all right. I think that's all about Dr. Hasliza's introductions. Let's invite Dr. Hasliza to present her keynote speech. Okay, the floor is yours, Doctor.
Thank you very much, moderator. Can you hear me?
Yeah, it is clear.
Okay, thank you. So first of all, thank you. Assalamu alaikum and very good morning.
Waalaikumsalam.
Thank you for your invitation for me to become one of the speakers for your conference. This is the first ever conference in UMRAH University, if I'm not mistaken. So what I would like to share with you today is what we have done in UBD on green chemistry for sustainable future. We're going to look at solar mediated hydrogen from renewable sources. So I'm from Center of Advanced Material and Energy Sciences in UBD. So the reason why we're doing this is because we try to harness solar energy, basically try to produce hydrogen production. We focus on three different aspects. First, we're going to tackle on renewable energy. And then second, for the clean fuel, at the same time, we try to look at biofuel sources. So the reason why we want to do photocatalytic hydrogen production from biofuels is because first we want to see if we can be able to convert biomass, normally biomass waste, to hydrogen production through photocatalytic reaction. And second, can we utilize photon energy from solar to catalyze hydrogen production. And second, can we release hydrogen gas from a sustainable and renewable source? So the advantage of solar mediated hydrogen energy is because it's the environmental sustainability, because we don't rely on fossil fuels to promote circular economy. And second, the carbon neutrality. So we can achieve carbon neutrality, carbon zero, and then we can contribute to climate change mitigation. First is the energy security. Then we can diversify our sources of energy, not only depending on foreign imports. And second, this is economic benefits. We can generate technology that can foster new innovation and also create new job opportunities. So now when we talk about hydrogen generation from water, basically hydrogen from water has been in commercial practice using steam reforming process, which is, if you see here, I'll try to get my laser pointer works. It's methane with water at very high pressure and high temperature to give us hydrogen and carbon monoxide. The combination of hydrogen and carbon monoxide, this is the building block in Fischer-Tropsch process, or we call it as the syngas industry, synthetic gas, and this will be used to produce a lot other type of product, for example, methanol and so on. But hydrogen in this process require higher energy. And then basically, if we can try to generate hydrogen from water only, that we call it the water splitting, utilizing solar energy will give us a milder condition for this reaction. And we can conduct them at ambient temperature, and we use energy from sunlight. So however, the problem with water splitting, they are not a straightforward process. The activation energy is quite high. And then currently the famous semiconductor to conduct the experiment is titanium. It only can absorb light in 5% region. So when we do that, there is a three challenge when we want to do conversion of biomass waste into hydrogen production. First is the catalyst development. We have to optimize catalyst development. There is a change from development from relying on precious metal into much cheaper and abundant materials. And secondly is the energy optimization. Can we improve the efficiency of photocatalytic process to maximize hydrogen production? And then and finally we can do the benchmark. For some reason, okay, this is scale up development. And then we can do the catalyst development process. This is the first part of my talk. We're going to look at how we can can produce hydrogen production using different type of catalysts. In this case, we use palladium titanium. And then the setup that we have in our lab. This will give a solar simulator. And then we already tested a different type of catalysts, palladium, gold, iridium, platinum. And if you see that, they are all very expensive precious metal catalysts that we deposited on titanium. This is the beginning of our process. We look at different type of catalysts to see which one can give us a lot more hydrogen production. And then we also look at different type of structure, determine the activity of this catalyst in increasing hydrogen production. But the problem with water splitting, we have this inefficiency, which is a back reaction process, which is the hydrogen and water, if we produce, will react back to give back reaction, which is we're no longer going to produce hydrogen. And the titanium itself, if you can see that it have a poor frequency window, it only absorbs 5% of solar energy. And that's the reason why we always introduce methanol in our system, basically to generate more hydrogen and prevent backwards reaction between hydrogen and oxygen. So this is what we have published previously that we've tried to challenge. There is a lot of concern when we're using palladium as a catalyst. So we try to reduce the amount of palladium that we use because the palladium is very expensive material and the prices keep on increasing. But whether we like it or not, palladium is very active. It gives us high amount of hydrogen. So what we are doing here, we try to use a very minimum amount of palladium. In this case, it's only 0.1%, 0.6%. But we can maximize the efficiency by controlling the palladium particle size. In this case, we use immobilization using colloidal process. And then we control the temperature of deposition at 1 degree Celsius, 25, 50, and 75. What we saw, if we reduce the synthesis temperature to 1 degree Celsius, we managed to produce a very fine nanoparticles on titanium with the average diameter is around 2.5 nanometers. But when we increase the temperature at 275, then we can see we have a very big distribution. And then we got approximately 5 nanometer in diameter. And how this, we further confirm our palladium coordination number using EXACT. This is very cutting edge characterization method that gives us understanding of the palladium coordination number and also palladium oxide coordination number. So basically it tells us that the coordination number will increase when we increase the particle size, and it correlates well with our TEM data that shows that we can actually control the particles of palladium even though we have the similar palladium loading. So variation of coordination number will tell us that it have a large number of palladium nanoparticles. So how that translates with hydrogen production, and then we can clearly see that in this figure. When we have our catalyst synthesis at 1 degree Celsius, we have a high amount of hydrogen being produced to reach 700 macromole in 3 hours. And then as we increase the temperature up to 75, the catalyst that we produce is very poor. to give only 200 micromole of hydrogen in 3 hours. There is a good correlation between the particle size and hydrogen production. And then we try to really understand why is this the reason, and then we plot the palladium-2 plus and palladium-O oxidation number with the rate of hydrogen production, and we can see that is a clear correlation between the particle size and hydrogen rate. And what we can see, when we have a low particle size, small particle size, most of the particle size will serve as an active site for hydrogen production. However, when we have a large particle size, we become recombination center because the particle size is long enough. The electron takes a long time to travel to the surface, and then it will give them opportunity to recombine with whole, and then cause us recombination, become a recombination size. And then we also look at metal loading dependency on hydrogen productivity. Then when we plot the hydrogen production and when we plot the hydrogen production with amount of loading, and we can see that basically it will drop in the amount of hydrogen production when we increase the loading. That can be the reason why it's because the enlargement in particle size. But if we try to maintain the particle size at 3 nanometers throughout the loading, surprisingly that it does, the stability is, the hydrogen production is basically quite similar across the loading. It means that loading is not important. What important is particle size. Then we can reduce the amount of palladium that we use in our catalyst, provided that we manage to control the particle size up to down to 3 nanometers only. And then this has been Arvind and I've showed that before. We're going to look at the mechanism of the reaction. Basically, when we have this reaction, methanol will quickly decompose on palladium, saturating the surface with carbon monoxide, and then this carbon monoxide will react with water to give carbon dioxide and release hydrogen gas. And then this process will be continuous, the cycle, and it shows that very high stability of the catalyst. Now we go to process optimization. Sorry. Okay. So it's raining in Brunei. I hope it doesn't interfere with the audio system. But now we look at what we did next is we look at different types of alcohol, try to really understand how the reaction happens. So we start with ethanol, methanol, propanol, butanol, different isomer of butanol. Then we can see that there is a trend in hydrogen production. Some alcohol will give us a lot of hydrogen, but some, for example, tertiary butanol doesn't actually give any activity. And then we move to complex alcohol. In this case, we look at cyclohexanol, benzyl alcohol, glucose, and sucrose. And we can see that when we have a cyclohexanol, the hydrogen production really, really low. And we have a benzyl alcohol in the type of aromatic alcohol. Basically, it's not active at all. So we understand that alcohol hydrogen is very important. What is alcohol hydrogen? The hydrogen that position on carbon that attached to hydroxyl group is very important to know that if this alcohol is going to be active or not in generating hydrogen production. Now we've done a lot of mass spectroscopy analysis, try to figure out what are the products that we saw when we generate hydrogen production. For example, when we have a primary alcohol, we're going to have a 2 mole of hydrogen gas. Or when we have a secondary alcohol, we only get 1 mole of hydrogen gas. And then we have a tertiary alcohol. Surprisingly, there is no hydrogen being produced. And then when you have a diol and triols compound, what we can see, we actually produce high amount of hydrogen. And the same thing with when we have a CH2 group, and then we got a lot more hydrogen production. So this is the trend that we saw when we look at different types of alcohol, and this gives us understanding on the mechanism of the reaction. Now, when we have photocatalytic reforming of biofuels, this is what I've showed before. Our mass spec saying that when we have methanol, we produce hydrogen and carbon dioxide. But when we have ethanol, propanol, we also produce this kind of like hydrocarbon products, which is for ethanol, we have methane, propanol, we have ethane, and so on and so on. What does this tell us? That all oxygenates with alpha hydrogen in the structure is actually photoreformed with water to produce hydrogen and CO2. However, when we have a longer chain alcohol, this will not going to be contributed into hydrogen production, but instead we're going to produce alkane product. So this is when we plot everything, and then we can come up with the 4 different rules to identify the activity of alcohol or any precursor that we did. So this is the insight into reaction mechanism. So you can see that we plot the hydrogen production per stoichiometric number. So all this alcohol is not active. The reason why there is no alpha hydrogen atom in the position to be active for oxygen production. So this all alcohol, this compound doesn't actually have alpha hydrogen. So I mentioned again, this is hydroxyl group. Alpha hydrogen is hydrogen that attached to the carbon. But when we have this alcohol, regardless of the long chain structure, they will produce a stoichiometric reaction, which is because the beta hydrogen in longer chain alcohol will not going to evolve as hydrogen production, but they will undergo decarbonylation. And if you have any methyl or alkyl compound, they will dissociate further. Sorry, in the secondary alcohol, it will dissociate further into hydrogen production. So this is the 4 mechanistic roles when we look at different type of alcohol and how they actually going to convert into hydrogen production. So the alcohol undergoes dehydrogenation and decarbonylation, and then at alpha carbon-carbon scission, and then they will remove the alpha hydrogen, but CO will fusion palladium will only be removed through photo-oxidation process. So that's done. We look at different type of alcohol, try to understand that. Now we move towards the biomass as the precursor. Can we extract as much as hydrogen from them and try to understand hydrogen from cellulose and sugar from cellulose. So we look at different type of cellulose. In this case, we start with cotton cellulose A, and then we also have this cotton cellulose cellulose from the fern fiber. And then we also have cellulose from fern fiber. And then we also have cellulose from coconut husk and cellulose from coconut husk. This, we extract them in our laboratory, and then we can compare from the SRD the degree of crystallization, crystallinity of all this type of cellulose. And then we also did some FTIR analysis to confirm the presence of cellulose and hemocellulose. So the thing that is quite interesting is when we have the band at 660, is a hydroxyl group that tells us we might have some hydrolyzed fragment of cellulose. And then we also have this group at 1732 that only appeared on coconut husk holocellulose. It means that in holocellulose you have this acetyl group that indicates that we don't only have cellulose, we also have a mixture of cellulose and hemicellulose. And how that all these cellulose give in terms of hydrogen production. Now we can see that this is hydrogen production from cellulose, from cotton, and then very high hydrogen production when we use palladium on titania. But when we try to use the cheaper metal, in this case copper and silver and nickel, basically they have some activity but not as good as palladium. Then when we concern about palladium as noble precious metal, we try to control, reduce the palladium loading from 0.3 up to 0.03. Interestingly, they are basically have similar hydrogen yield. That means that we can actually try to reduce our palladium content. It doesn't have to be 0.5, 0.3%. We can actually reduce them again to very low palladium. As long as palladium is there, we can control the particle size as I mentioned before. And then how hydrogen production affect when we vary the cellulose precursor, cellulose content linter from coconut husk and from fern fiber. Then we can see that cotton gives us high hydrogen production, and then followed by cellulose and from the fern fiber. But when we vary the amount of cellulose, we can clearly see that the cellulose, the hydrogen production definitely relies strongly on the amount of cellulose that we put on our photocat reaction. So this tells us that yes, we can extract hydrogen from cellulose. It's not something that really difficult. But another step that we can do, can we get hydrogen from sugar that we derive from cellulose? So in this case, we hydrolyze our cellulose using hydrothermal method, and then we basically break all this polymeric cellulose bond into a sugar that contain glucose and fructose. And then from the liquid mixture, we conduct them in photocat experiment, and then we can definitely see how much hydrogen being produced. So interestingly, the liquid product that we get from the cellulose that been treated give us much more hydrogen production compared to the liquid compared to the cellulose itself. Even copper titania basically give us a much high amount of hydrogen compared with the copper titania that we use only on cellulose. And then now we move again. That one is cellulose from biomass. waste. Now can we get hydrogen from solid and liquid waste, liquid food waste? Okay, basically in our everyday experiment, everyday life, we will remove or we will discard most of our food waste to our bin. But can we check, in this case, we look at chicken bones, and we can look at also rice dry that has been dried. And then we also look at this residue from chili. It's either from the seed or from the stalk of the chili. So what happens is we dry them for 2, 3, 4 days, and then we blend them, and then we use shaker to make sure we got a very fine powder. And we can use this in our hydrothermal reaction. So what we did, all the powder that we produced, we put in our hydrothermal chamber, and then we position them in our furnace here, and then we let the pump to keep on pumping, pressurize the system to reach our a very high pressure. And then we can increase the temperature up to 240. So by having high temperature and high pressure, we managed to control the water from having from become vapor, but basically high pressure and high temperature water, but still as a liquid. So this gives the water to act as an acid, H plus and OH minus, to basically hydrolyze our food products, food waste into liquid products like this. So this liquid product will be used as the liquid solution for our hydrogen production in photocatalytic reaction. So just the preliminary data that we've got now, when we have a rice waste that has gone bad, and then when we get the water from that, what we can see that we managed to increase hydrogen production when we control the hydrothermal treatment from 5 minutes up to 30 minutes. You can see that 5 minutes, no hydrogen being produced. When we increase the hydrothermal treatment up to 30 minutes, and we can see that we increase the hydrogen yield up to 125 millimole per gram of catalyst. The same thing with chili waste. At the very beginning, there is no hydrogen produced, but when we increase the hydrothermal temperature, hydrothermal duration up to 30 minutes, and then we can see the liquid that we get from the reaction will give us high amount of hydrogen production. It's not just from that, then from cotton as well. This is cotton from our fabric that no longer being used. We also treated them. Now what we can see, the amount of hydrogen being produced is very high, which is 749 millimole of hydrogen per gram of catalyst. And then with triggered bond as well. So this gives us indication that you can use different type of waste. It's not just from your food waste, for fabric as well, even from the wood, that we can treat them and then use them as a precursor to generate hydrogen production. So we don't have to rely on our alcohol or any synthetic chemicals. And then interestingly, we also look at hydrogen from liquid that we got it from rice that has been washed or soaked. So there's 3 types of treatment that we did for the rice. First, the blue one, when we as an Asian people, we always eat rice. Basically, we wash our rice every day. So when we collect the first wash of rice, the water that we get when we first wash in the rice, and then we test them for hydrogen production, they are not actually very promising. And then when we cook our rice and then we get the water from the cooked rice, interestingly, we managed to get high amount of hydrogen. But when we soak our rice overnight and get the water from that, the water that we discard, when we can use it as a precursor, as a feedstock to generate hydrogen production. This gives us an array of possibilities that we can generate hydrogen sustainably from different type of waste that we get it locally in our country that we reside. So first we can rely on biomass, from the cellulose from biomass waste, and then we also from food product that we get in our from our kitchen, that we can convert them into material or liquid solution that we can use to generate hydrogen production from photocatalytic process, which does not require any energy from sun. So then conclusion, it's very brief talk, but if you're really interested in this type of project, you can always contact me. I can just Google my name, Hasliza Baruji, will come up. There's only one Hasliza Baruji in the world, so you will come up to my website. So basically the conclusion that I would try to emphasize is how we can achieve a circular economy cycle. We don't have to throw our waste, we can repurpose them, and then we can use that to generate our hydrogen production. So we try to highlight the role of photocatalytic process to produce hydrogen that's not rely on any energy, but basically we rely on solar as a source of energy to drive the process. So basically, if we combine our photocat experiment with hydrothermal treatment, we can achieve high hydrogen production. So now this is acknowledgement. This is all the team member in UBD, and I would like, this is basically project that has been conducted by my student Shahida and also Humaira. I would like to invite everyone in the university, in UMRAH University, if you have master and degree in chemistry or any other related field, please, we opening PhD scholarship to UBD sometime in February next year. So please look at our website, and if you're interested, please come and apply for the position. There is a monthly living stipend for you to apply to UBD. Okay, that's all for me. So I'm going back, give back to the moderator. Thank you.
Okay, thank you so much for the insightful presentations. Ladies and gentlemen, now we come to the Q&A session. Yeah. Then I invite the audiences in this room, offline audiences or online audiences in the Zoom meeting room to ask questions. Yeah. Then you may use the chat box to write down your questions there, or the audiences in this room, you can raise your hand and then mention your questions. Yeah. Maybe in the Zoom committee can help me to check the questions in the chat box. Okay, any questions, guys? Everybody from this room?
Hello, Dr. Hasliza.
Yes.
Yeah, I'm Dr. Sikin from UKM. It's very interesting about your analysis using ISAF.
Yes.
Where is the location for this analysis? Is it in your university?
No, in Asian, there's only one place. You can extend them in Thailand. They have this diamond facility. But the one that I use in the UK with my collaborators. Yeah, we don't have, I mean, this is, exam require very high intense X-ray radiation. It's not just like FRD.
Yes.
So basically you need like strong energy to generate the high extended X-ray radiation. In Southeast Asian, there's one in Thailand, but I haven't been used that. But I'm pretty sure they're open for people to send some sample. But the one that I use in Diamond, Howell, UK. Yeah.
Okay, thank you.
Welcome.
Okay, thank you for the questions. It seems that we have another participant that want to ask questions. Yeah, someone's raising hand in the in the Zoom meeting. Yeah, you may open your microphone, and if it is possible, you may turn on your camera devices. Yeah, the first change may be echo.
Yes, sir.
Yes, sir.
Yeah, is it echoing? Okay, hello, echo. Are you there? Or we can give a change for another participant first. Maybe some technical issue with echo. Oh, we go to the offline participant first, Dr. Hasliza.
Okay.
Yes, please.
How can chemical solution help
Pardon me,
improve
you
the?
may mention your name first, maybe.
Name. My name is Gadiza Aulia Zahwa. I'm from chemistry program study chemistry. How can chemical solution help improve the efficiency of right oil extraction from field with high water content or deflator to rice layers?
Oke.
Jadi bagaimana bahan kimia dapat membantu meningkatkan efisien ekstraksi minyak mentah dari lapangan yang memiliki kandungan air yang tinggi atau lapisan yang sulit dijangkau? Thank you.
Translate the question. Is it clear, Dokter? Dr. Hasliza?
Saya tak berapa faham lah soalannya apa.
You may come again. Boleh diulangi?
Macam mana nak extract apa minyak tanpa air?
Okay.
I don't know.
Ya, kita
Is it
ulangi.
betul? Macam mana nak
We will repeat. We will repeat, Dokter. Dr. Hasliza. Sekali lagi boleh pertanyaannya? Pelan-pelan boleh.
Bahasa Melayu pun tak tahu. I will try to understand.
Bagaimana bahan kimia dapat membantu meningkatkan efisien ekstraksi minyak mentah dari lapangan yang memiliki kandungan air yang tinggi atau lapisan yang sulit dijangkau?
Oh, I don't know. To be honest, macam mana nak jawab? It's not my field. Macam mana guna, I don't know. To be honest, I have no idea how to answer that question. I don't think it's related to my talk. Macam tak sama untuk talk saya.
Okay.
Yeah, my process is I try to extract sugar from food waste. This is what I did. But how to extract, I don't know, chemical from the field, from lapangan, apologize, I have no idea how to do that. But I'm pretty sure other people might be able to answer your question. Sorry about that.
Oke, tidak berkaitan dengan pembahasan sepertinya ya. Tidak apa-apa. Thank you so much for the question. Another question. Oke, silakan.
Okay, introduction. My name is Ziva Zain. I'm from Chemistry Study Program, and I will ask for you, how is the concept of sustainability applies to the anti-heterogen production claim based on solar energy from technology design to environmental impacts? Maksudnya adalah bagaimana konsep keberlanjutan diterapkan dalam seluruh rantai produksi hidrogen berbasis energi surya, mulai dari desain teknologi hingga dampak lingkungan. Terima kasih.
Is it clear, Doctor?
It's a very complicated question. I don't know how to answer that. Moderator, can you simplify in the normal sentence what is the question again?
Okay, maybe I need to hear the questions again, then I can simplify it.
It's too sophisticated, the question. Did you using ChatGPT to get the question? It's very hard for me to really understand.
I don't know. Okay, let's hear the questions again, once again. I'm gonna have to simplify as much as I can. Basically, I'm not from chemistry, so also it's hard for me. Okay, ulang.
Oke, bagaimana konsep keberlanjutan diterapkan dalam seluruh rantai produksi hidrogen berbasis
bagaimana
konsep keberlanjutan diterapkan dalam seluruh rantai produksi hidrogen.
Can we stop there? Boleh di-cut nggak pertanyaannya sampai situ? Boleh. Oke.
Oh, macam mana?
Okay.
Make sure the technology is fully integrated.
Okay.
Well, the hydrogen production has been produced basically from steam reforming. They have all the integration system. Methane will get in, and then they will have water, and the hydrogen being produced will be piped, or maybe they will normally in Brunei they have. They're using certain chemical, if I'm not mistaken, toluene as the hydrogen storage. Then from basically the hydrogen storage material will liquefy hydrogen gas, and then it give them flexibility for transportation of hydrogen. Basically, that's what I can say. hydrogen production from in industry has been conducted for a long time. Just that now we try to shift from using electricity and from relying on methane as a fossil fuels into a much more sustainable and renewable process, which is we rely on solar. At the same time, we rely on waste, for example, food waste and bio waste. That's what I can say. I hope it's answered the question.
Okay, I think it's already answered the question. Is it clear?
Oh, yes. Thank you so much.
Okay, thank you so much, Dr. Hasliza. Then, how about online participants? Anybody want to ask questions? You may raise your hand and open your microphone. And if it is possible, you can turn on your camera. Oh, another participants from offline, from this room, Doctor. Silakan.
Okay.
My name is Farol Fahrezi. I am from program study chemistry. My question is, what are the main challenges in improving the efficiency of photocatalytic or photoelectrocatalytic process in hydrogen production using solar energy? Apa tantangan utama dalam meningkatkan efisiensi proses fotokatalitik atau fotoelektrokatalitik dalam produksi hidrogen menggunakan energi surya? Terima kasih.
Okay, I think it's clear.
Okay, it's clear. Thank you. Untuk hasilkan hydrogen menggunakan photocatalysis memang banyak halangan. There are so many obstacles. The first one is yang pertama solar. Normally, semua catalyst only absorb around 5% up to 10% maximum of solar energy. So kita ada lebih 80% tenaga daripada solar yang tak digunakan untuk hydrogen. Satu, itu challenge pertama. Yang kedua, high activation energy. Untuk water splitting, you require high energy. And then this normally will be hampered by the poor catalytic performance and also back reaction. Back reaction ni, apa yang saya maksudkan, kalau kita buat water splitting, water terhasilkan hydrogen gas dan oxygen gas. Hydrogen gas dan oxygen gas ni, kalau kita tak pisahkan immediately, dia akan ada reaction balik semula dan hasilkan water. Ini will also reduce our hydrogen production. And then thirdly, catalyst also deactivate over time. And fourthly is the yield of hydrogen yang kita hasilkan masih terlalu rendah kalau dibandingkan to steam reforming process. If we compare the hydrogen that we get from water splitting using photocat reaction, it's very, very low compared to the industrial process using steam reforming. Yes, the challenge is a lot. It's still a very preliminary process. There is no commercial practice already available for water splitting using photocat reaction. But hopefully in the future, we're basically going to get it done using a different type of solar active materials for water splitting. I hope it answers the question.
Okay, thank you, Dr. Hasliza, for the questions. Is there any other questions from the audiences? Oh yeah, another questions, Dr. Hasliza.
Okay, sure.
Silahkan.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Let me introduce myself. My name is Marcella Audiatati from Chemistry Study Program. I want to ask, what are the economic and technical challenges that need to be addressed to make solar energy-based hydrogen technology a commercially viable energy solution? Maksudnya, sejauh mana penggunaan bahan kimia dapat meningkatkan stabilitas dengan efisiensi dalam proses geothermal, terutama dalam menghadapi penurunan tekanan atau suhu yang tidak stabil. Thank you.
You got the question, Dr. Hasliza.
Macam beda je the English and Malay translation.
I think so. So we're gonna clarify which one is the question exactly.
Which one is your question? The English one or the Malay one? I think the most related to my stock is the English question. Ask me the English
Okay,
question.
maybe we're gonna answer the first question. Then. Pertanyaan yang bahasa Inggris
Ask
atau
me
yang bahasa
again.
Indonesia?
Read again the English one.
Boleh yang diulang yang bahasa Indonesia.
What are the economic and technical
Bahasa Inggris maaf. Ya, boleh. Silakan.
What
Bahasa
are
Inggris,
the
ya.
economic and technical challenges that need to be addressed to make solar energy-based hydrogen technology a commercially viable energy solution?
Yeah.
Thank you.
The challenge, I think because the challenge is must be on political policy. Because as I said, hydrogen from industry using steam reforming, it gives us a lot of hydrogen. It will not gonna be similar to the amount that can be supplied by photocat reaction. So what it needs to be done, I think, is the political policy, the policy from every government or every industry to rely on renewable hydrogen. That's only the commercial hydrogen production for photocat can be basically using commercial, can be commercialized. The reason why, like I said, hydrogen from photocat is very small. It's not going to be sustained as much as it requires a lot of input in terms of policy, in terms of money, in terms of investment, and the government policy will definitely help to shift from our relying on water from steam reforming towards a clean photocat process. Basically what I'm saying, kita ada campur tangan daripada government dan polisi daripada government untuk semua orang kena shift daripada energy daripada fossil fuel kepada energy yang lebih bersih using solar and water splitting. Okay?
Okay, thank you so much, Dr. Hasliza. Dan maybe for the last questions or the next question, we gonna check the online participants. Is there any questions there, committee? Can you help me to check? Okay, no questions from online participants, Doctor, and also there is no other questions from offline participants. It seems that we're gonna come to the end of this session. Okay.
Okay.
Yeah, thank you so much, Dr. Hasliza, for sharing the insightful presentations about today's topic. We hope that we can meet in another conference, maybe, or in another event
Inshallah.
at a time. Okay.
Inshallah. Thank you.
Yeah, have a nice day, Dr. Hasliza. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Okay. Ladies and gentlemen, I think that's the end of the third keynote speakers for today. And then we're gonna move to the next keynote speaker. Let me check. Dr. Nurul Asikin Mijan already here. Hello, Dr. Nurul.
Yes, I'm here. Yes,
Yeah,
I'm
okay,
here.
all right. Let's kick off the agenda. So, Dr. Nurul, you're gonna have 25 minutes to do your presentations, and after that, we will come to the Q&A sessions. Yeah, you may share your own screen, and then before coming to your presentation, I would like to read your short biography. So, ladies and gentlemen, our next keynote speaker, Dr. Nurul Asikin Mijan, received her PhD in chemistry from University of Malaya in 2018 and joined University of Putra Malaysia as postdoctoral researcher in 2019. And her specializations are in organic chemistry, analytical chemistry, catalyst, and kinetic and mechanism. And then the scope of her research are in organic chemistry, catalysis, yeah, renewable energy, material chemistry, and nanotechnology. And if we want to meet Dr. Nurul in person, we can come to Department of Chemical Science, Faculty of Science and Technology, University Kebangsaan Malaysia. Then Dr. Nurul already received a lot of award,
And the latest award is Anugerah Perkhidmatan Cemerlang in 2024. Yes. And then another award is Anugerah Kecemerlangan Mira Prestasi 2022. And all, of course, Dr. Nurul have published a lot of research and articles, yeah, related to his specialization. Okay, now let's invite Dr. Nurul to the stage and present her presentations today, keynote speech today. Dr. Nurul, the floor is yours.
Okay, thank you. Can you see my slide?
Yeah, we can see your slide.
Okay. Assalamualaikum and very good morning. Still morning, I'm not sure. But I'm sorry, I'm not feeling very well actually. But I'm doing my best to give a presentation about our topic today, entitled on the turning vegetable oil and waste into the sustainable energy, which is I will focus on the production of liquid biofuel from the biomass, liquid biomass. Okay, before that, let me introduce my university first. So I'm coming from University Kebangsaan Malaysia, located at Bangi. UKM is a very beautiful university. We are inside we are surrounded with a forest, a lot of tree. Jika datang masuk ke UKM, you akan rasa tenang, but you need to be worried. We have a lot of animal also. So I check the distance from Tanjung Pinang to UKM. If by car, maybe we have a boat, ferry. So it takes 11 hours from Tanjung Pinang UMRAH. And then, as I mentioned before, if you come here, you need we will have see that UKM surrounded by the forest. So we have a lot of very credible monkey. So, but they are very kind of naughty, but very comel. Okay, so if you come to UKM located at Bangi. So here is a kind of destination you can go. If you come here, you can go to KLCC. You can go to the famous chocolate factory from Malaysia, which is Beryl. And then you can go to the Genting Highlands. It's about 80 kilometers. And then we also are very near with the Putrajaya, around 13 kilometers. And since that Bangi also very close to KL, near KLCC, so we are also close with the Bukit Bintang. So without further ado, I'd like to talk about my topic today. So I think that no need for me to introduce why we need to have alternative energy, since that from our first speaker, from our second speaker talking the same thing. So you can see that we need to have a biofuel as a replacement for the petroleum derived fuel. Okay, and then for the second speaker today, Dr. Rustam explained about the biomass. We need to we need to produce biofuel from the biomass. Yes, the same thing like Rustam. In this project, we use biomass as a biofuel, as a feedstock. Why? Because biomass currently offer the only sustainable sources of organic carbon, which in turn it can easily obtain large availability from the surrounding. Is also environmental friendly, since biomass is considered as a waste, so we can get in very cheap price. Have low maintenance, since biomass contain a lot of organic carbon. It contain a lot of high energy content, so that's why it have full flexibility. And of course, since it have a lot of energy content, it will have high efficiency. So in this one, we have a lot of various type biomass sources. we have sewage, we have animal residue, we have biomass from the forestry, we have from the industrial residues, and then here I would like to focus on the agriculture crop biomass. So we have a kind of wood chips, we have kind of we have kind of oleo feedstock, and then from this oleo feedstock we can transform it to biofuel and then utilize for our our transportation. So a lot of biomass I mentioned before, but in this project I would like focus on oleochemical feedstock, which is focused on waste oil and fats. So oleochemical feedstock such as waste oil and fat, why I choose this one, because of the main component of this kind of feedstock is triglyceride, or we can call it as TAG. Not wanted to mention that the TAG or triglyceride mainly consists of fatty acid change. If you look from here, the TG structure, each TG structure contains 3 fatty acid change. Okay, so meaning that 85% of TAG comprise of fatty acid if we deduct the propane unit. Okay, so fatty acid are sustainable feedstock and can be obtained from different sources such as vegetable oil and animal fats. Since there are various types of biomass derived biofuel which have been successfully produced by our team before. Here is an example. The production of biofuel we work is production of biodiesel. It's kind of methyl ester content, fatty acid methyl ester, still contain oxygenated species. And then we also producing the same thing like our second plenary speaker, produce a green diesel, biojet fuel, and also green gasoline. What is the difference between 3 of them? Actually, the similarities of the 3 type of biofuel, the structure of green diesel, biojet, and green gasoline comprise of straight chain hydrocarbon. But the difference only the length or the numbers of carbon. For the green diesel, usually the carbon from C9 to C23, biojet C9 until C16. Green gasoline is considered very short chain biofuel, which is C until C12. Okay, when we compare this kind of biofuel with petroleum-based fuel, actually for the petroleum-based fuel mainly comprise 75% of hydrocarbon. Meanwhile, and then mixed with the 25% of aromatic hydrocarbon. So since that the green diesel, biojet, and green gasoline comprise of 100% of paraffin, so it should meet the physical characteristics, the physical properties of the green diesel, biojet, green gasoline will be similar like petroleum diesel fuel. Here the table is a comparison between biodiesel, green diesel. You can see that yes, biodiesel meet some of standard for the petrol diesel properties. However, the biodiesel have some drawback which is related with the oxygenated species, so it will affect on the oxidative stability. So if we store the biodiesel at longer period of time, so the biodiesel can be deteriorated to something else. Instead of green diesel, since it have no oxygen content, so the green diesel can be stored in longer time. It's similar with the petrol diesel. So when we look at the cetane number for the green diesel kind of energy content, so green diesel also have much better cetane number as compared to biodiesel and petrol diesel. That's why in our team we focus on production of a green diesel. Before that one, let me touch on the production of biodiesel first. So in this speech today, I would like to talk 4 types of feedstock. The first one, we will focus on the soybean oil. Second one, we focus on the waste oil, low quality of oil, waste cooking oil. And then we go to the palm kernel oil. And last but not least, we will go to the fat oil grease, or we can call it as FOG. So soybean oil into the biodiesel. So this project have been done by my student Salim Makoda Elukat from the Algeria. So currently this publication have been published in Energy Conversion Management. So why she choose soybean? Because yes, soybean, from this graph we can see that the production of soybean considered second largest than the palm oil. Okay, so since that the soybean have a large production, so that's why my student focus on the conversion of soybean to biodiesel. Okay, so this is the properties of soybean. You can see from here that the soybean considered very refined. The FFA content is very little, which is 1.26. So however, in this soybean, they mainly comprise oleic acid and linoleic acid. So utilization of soybean in the engine will not be in the good in the good choice, because of direct utilization of this oil will damage the engine, because of it have higher viscosity and also it have a lot of oxygenated species. My students start to convert the soybean into biodiesel. So what is biodiesel? Is monoalkyl ester of long chain fatty acid. Okay, so it can be produced by trans-esterification. My student utilize calcium oxide in order to convert soybean oil into biodiesel. Okay, so this is the catalyst. So what we will do, the catalyst will be mixed with the methanol and then mixed with the soybean. And then after that, she will heat up the reaction, and then what we will get a mix of the glycerol and also our biodiesel. Okay, and also our methanol. After heat up at certain temperature, we will remove the methanol. So what left is our biodiesel. So this biodiesel we can use directly in engine, in the diesel engine. Okay, so this is the which have been used in order to convert soybean oil into biodiesel using calcium oxide but modified with the molybdenum and zinc. So when she do the when we look at the biodiesel conversion here, this catalyst, the MO7 zinc 3 mixing of molybdenum 7 and zinc 3% give highest conversion of soybean into the biodiesel. So, and again, she also focused on the optimization study. She studied on the methanol, whether methanol can improve the biodiesel conversion, utilize a lot of catalysts, studied period of time, studied impact of reaction temperature, and then what she got is 90% of biodiesel can be obtained using 50-to-1 ratio methanol and oil ratio within 2 hours at temperature 60 degrees Celsius using 1 weight% catalyst loading. So from what she got from here is majority of the kinematic viscosity, flash point, pour point, and clock point, kinematic viscosity and flash point meet the standard for the petroleum ultra low sulfur standard here. However, what I want to emphasize, since that as I mentioned before, that biodiesel, even though that biodiesel considered ideal and has been commercial widely nowadays for as a diesel oil, however, the main problem about biodiesel is winterization properties related with the cloud point and pour point. So it have bad clock point. So meaning that this oil cannot be sustained if we use it at the temperature cold condition. Similarly with the pour point, so it will have low temperature fluidity, especially at cold temperature. So that's why that's why I move on to the project production of new biofuel known as a green diesel, like second speaker. So okay, in this topic we already complete the project, transform the waste cooking oil into green diesel, and then this finding also have been published a lot from my team, and then especially published by Dr. Abdul Karim Al Sultan. So why we choose waste cooking oil? Because what is waste cooking oil? Waste cooking oil is a cooking oil that has been discarded. So usually it have high FFA content. So you can get waste cooking from the various sources. Example, household, restaurant, fast food. And then if we throw this waste cooking oil, of course, it will pose environmental risk. So that's why we need to mitigate this kind of behavior. Instead of throwing the waste cooking into the environment, so why not we utilize waste cooking as our feedstock, as our green diesel feedstock. So instead of producing biodiesel, those who have a problem for the winterization properties, why not we producing something which is similar with the petroleum fuel, which also known as a green diesel. Okay, so that's why we choose waste cooking in our project, and we produce a green diesel as our product. So what is a green diesel? Green diesel can be produced by one reaction known as deoxygenation. In this deoxygenation, there are two pathways, which is the first one will be decarbonylation and the second one decarboxylation. So these two pathways, what happen? The fatty acid will remove either CO2 or carbon monoxide or carbon dioxide and water as a byproduct, and produce straight chain hydrocarbon, whether unsaturated hydrocarbon if decarbonylation, or straight chain alkane if decarboxylation. So noteworthy to mention here, in this project considered very economic because we can produce fatty acid to green diesel at lower temperature, 300 or 300. We able to produce green diesel at temperature 250, 300, 350, and then majority of the green diesel properties meet petrol diesel standard and have no oxygen, have less oxygen content for the green diesel. So in this project, we utilize, this is example deoxygenation reaction setup. We use autoclave. So this is our waste cooking. We mix with our catalyst. We deoxygenize. So what we get, we will have two layers of product. So the upper layer will be our green diesel and bottom layer will be our H2O. Okay. So again, my project, so we focus on the optimization reaction. From the waste cooking feedstock, we able to produce more than 85% of the hydrocarbon with products selectively toward diesel, which is carbon 15 and carbon 17, around 93%. We able to achieve this at time 60 minutes using 1 % of catalyst at temperature 330 Celsius. So previously there is one question talking about what is the impact, impact of the green diesel as compared to petroleum derived fuel. Here I like to share something very interesting to clarify, to confirm that green diesel is a clean fuel. So in this part, we also studied on the emission testing for our green diesel produced from waste cooking. So what we do, first we need to blend our green diesel with petroleum diesel. So we blend, we make G5, meaning that 5% of petrol diesel and 95% of green diesel. We have G20, meaning that 20% of petroleum diesel and 80% of green diesel. So after blending, we will test it for the combustion testing. So what happened here? So we able to confirm that the blended form G20, the green diesel, are able to fully combusted in the engine as compared to petroleum diesel. Okay, when we look at the impact on the greenhouse gases, for example, like CO2 and also SO2 emission, we discovered that blended green diesel also give better lower CO2 and SO2 emission as compared to petrol diesel. So from this finding, we confirm that our green diesel is a clean fuel. Okay, why this happen? Because of complete combustion. Usually it will result lower carbon monoxide in the green diesel blending. Since that we able to push the engine to have complete combustion using green diesel, so that's why we able to reduce CO2 and SO2 emission. Since in the fuel also we don't have any utilization of sulfur species, so that's why our fuel also free from sulfur as compared to petroleum derived fuel. So other than waste cooking, we also try to utilize palm kernel oil as second palm oil producer. Malaysia, we produce a lot of palm oil. So instead of using refined palm oil, we are focusing using palm kernel oil in our project for production of sustainable aviation fuel, or we can call it as SAF. This project have been published 2002 and also 2024. Okay, so what is SAF? SAF, or we can call it as biojet fuel or kerosene. Jet fuel is an aviation fuel designed for use in aircraft powered by gas turbine engines. So jet fuel is a high quality fuel from road to transportation fuel. When you look at this one, actually the jet fuel comprise the hydrocarbon chain from C9 until C18. Why we want to produce SAF so much? Why we want to produce? And not wanted to mention that production of SAF now is considered trending. It's become very hot. We need to produce a lot of SAF. Even in Malaysia now focusing on production of SAF. Okay, so why? Because of we want to mitigate the CO2 production, and we have a lot of people also like to go in multi place around the world. So by what transportation? Of course by flight. So that's why SAF is very important in Delhi. Okay, so this is current commercial aviation biojet fuel have been utilized globally. This is example from the United Eco Skies, and then from the KLM powered this one, and also SpiceJet have been utilized SAF widely globally. Okay, and then a lot of feedstock, we can transform a lot of feedstock into biojet fuel, but there is a few type of SAF feedstock which is very ideal to be transformed as a jet fuel feedstock. The first one, palm kernel oil, and then second one, coconut oil, and last one will be palm oil. Here I want to focus on palm kernel oil, or we can call it as PKO. Why? Because of main composition fatty acid in palm kernel oil is C12. So once we carry out deoxygenation reaction, we will remove carbon monoxide or carbon dioxide meaning we will remove one carbon from our feedstock. Removal of one carbon will produce product selectively toward carbon 11. And we look at the change of the jet fuel is C9 until C16, meaning that C11 is within the range of jet fuel range. So that's why palm kernel oil is considered very ideal feedstock to be utilized as a main feedstock for transforming in order to transform that to biojet fuel. So here is the result from our team. We already transformed PKO into SAF. Yes, we got product carbon from C10 until C12, meaning that this SAF PKO selectively toward jet fuel production. Okay. Again, my student from University of Malaya. So we convert palm kernel oil and study the blending effect. Okay, so what we discovered is a lot of organic species inside the green diesel or in the south which been produced from PKO, example like paraffin, isoparaffin, olefin, naphthalene, aromatic, and others. So we want to highlight something here. Yes, alkene is desired product. Isoparaffin also very good as a SAF. Naphthalene also good, but there is two species which is not so good to be in SAF, which is olefin and aromatic species. Okay, so this is example of olefin. Okay, aromatic species, kind of aromatic like this, have unsaturated, have a double bond. So what is the impact of these two things? If we have a lot of aromatic in SAF, so of course it will lead the SAF during burning. When the fuel burn inside the engine, it will increase the production of soot. Soot kind of like particle lah, particle yang berwarna hitam. So dia akan why this one form because of incomplete burning. Even though because of incomplete burning. So however, even though that aromatic will increase soot formation, but we still need to have some aromatic species inside the SAF, which is within range 15 to 25 volume, in order to avoid leaking in the seal of fuel system. Okay, this is the impact of olefin. Olefin is contain unsaturated bond, is a very reactive class hydrocarbon. However, the same thing like aromatic species, it will result some drawback in the jet engine because it will result in formation of deposit in the jet engine. So that's why we our team, we do our best in order to reduce formation of olefin. One of the alternative by utilization by addition of hydrogen during the reaction in order to suppress formation of double bond here. So we will add another hydrogen, so we will get straight chain hydrocarbon alkenes. Even though that we able to produce SAF in many projects, but the problem what we found is the reaction process still very high, which is above 300. So my student, my PhD student Megan Shinye, we like to reduce the reaction, the oxidation reaction, at least below than 300. So what we do, we do deoxygenation using microwave irradiation system. So what is the impact of microwave? This microwave is very powerful technique. It can promote uniform heat during the reaction. So since it can promote uniform heat in one's time, so it will provide rapid responses for heating and cooling process. Once the heating is occur rapidly, so the reaction will occur fastly also, and then we can remove the CO2 and CO in within shorter reaction time. So here is a comparison between conventional using common method, and then this one is the method using microwave irradiation. Even though that we able to reduce the reaction at lower temperature, however, we admit that microwave irradiation doesn't give result on the production of on the selectivity of the product. From here, from the oxygen to hydrogen to carbon ratio, oxygen to carbon ratio, and hydrogen to carbon ratio, we discovered that microwave irradiation promote formation of shorter chain hydrocarbon, meaning that the microwave irradiation promote cracking reaction, so it will lead formation of gases and reduce the hydrocarbon yield as compared to conventional heating. So then we conclude that the microwave irradiation is less effective in removing oxygenate. From here, microwave irradiation, the oxygen to carbon ratio is much more higher as compared to conventional heating, is less 0.2. This one is close to 0.4, meaning that microwave irradiation contain more oxygenate species as compared to conventional heating. So we confirm that microwave irradiation is not a good alternative for deoxygenation reaction. However, microwave irradiation still can produce a lot of SAF product. So this one is the last feedstock we transform to SAF, which is fatty acid, fatty oil grease, or we can call it as FOG. So FOG we can obtain from the sewer grease. So this is the example we can get the FOG from the piping system pembentungan. This is example in the camera inside the piping. So do you know that accumulation of FOG, a lot of FOG inside the piping system will lead to the piping blockage, and then of course this kind of blockage at the same after longer time it will lead to the pipe corrosion to the sewer system, and then of course it will result leaking and then result in environmental problem. So this FOG is a byproduct accumulate inside the pipe. It considered as low grade feedstock because of it has high content of free fatty acid. Okay, so that's why in this project we utilize FOG for production of, we produce FOG, we use FOG for production of SAF also, and also as a green diesel feedstock. However, as I mentioned before that we have problem with the aromatic and also alkane species. So we want to produce SAF which is contain only straight chain hydrocarbon, no unsaturated hydrocarbon. So what we will do, we do the same reaction, deoxygenation reaction, but we add another hydrogen, which is we add during the reaction we will add hydrogen. So the hydrogen will promote addition of hydrogen. So what we will get is straight chain hydrocarbon. There is no double bond in our product. So this is what we want. Okay, so what we discovered, majority of the product obtained is C16 and C18, and then noteworthy to mention that surprisingly we also get a lot of formation of C14. So C16 and C14 is considered within range of the SAF. So yes, FOG we can transform FOG to the SAF. Okay, so again, since that we studied addition, we pause we want to remove the double bond inside the SAF product. So we studied the impact of hydrogen pressure. So what happened? Once we increase the hydrogen pressure, we also promote the hydrodeoxygenation to occur, and then we improve the hydrocarbon yield. we improve the hydrocarbon yield of our product. So what I want to say that high pressure have positive impact on the reaction and also on the hydrocarbon yield. Okay, so this one is the hydrocarbon product. We can see that majority of the pressure hydrogen from 1 MPa until 5 MPa can produce product hydrocarbon within range C13 until C17. So this one considered as SAF product, jet fuel product lah. Okay, so then okay. Okay, so the conclusion here, vegetable oil, waste oil, fat can be efficiently transformed into renewable fuel such as biodiesel, green diesel, and sustainable aviation fuel or SAF. Green diesel actually superior to biodiesel due to its higher compatibility with existing diesel engines and infrastructure as well as its superior fuel properties. And indeed, green diesel able to mitigate carbon monoxide and CO2 better than petroleum diesel. The desired carbon change length for the fuel actually depend on the key factor including that reaction catalyst, temperature, reaction atmosphere, either hydrogen or inert condition, and also that's all from me. Thank you.
Okay. Okay, thank you so much, Dr. Nurul. We really appreciate your opportunity to be here. We hope that you get better soon. All right.
I'm
Now,
sorry.
yeah. Now we come to the next session, Q&A session. I invite the audiences in Zoom meeting or the audiences in this room to ask questions. Yeah, you may raise your hand if you want to ask questions. Yeah. Committee, you can help to hand over the microphone. Okay, silakan.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam.
My name is Farol Fahrezi. My question is, what is the relationship between the chemical composition of biomass waste and the efficiency of biofuel production? Thank you.
Okay.
Okay.
Is it clear, Doctor?
Okay, what is the efficiency? Efficiency, yeah?
Yeah.
Efficiency, okay. What is the relation between efficiency and fuel production? Of course, it's close, the efficiency of the fuel close with the efficiency of the fuel. For example, if your oil comprised of shorter chain hydrocarbon like lauric acid C12, 12, kita buang satu jadi C11. 11 is jet fuel. Okay. You boleh gunakan that jet fuel untuk kapal terbang, untuk energy enough untuk bakar, untuk naikkan kapal terbang lah. Tapi that kapal terbang doesn't have large energy as compared to diesel. Diesel kita perlu macam lori, beban berat, kita perlu banyak energy, burn terus dapat gerakkan lori kan. So we need more high energy which is diesel. So kita kena cari feedstock yang lebih banyak longer chain, macam feedstock yang contain oleh acid, oleh acid, apalagi yang tinggi-tinggi lah, longer hydrocarbon chain. For example, C18, C19, C20. So nanti you remove satu karbon, dapatlah C17, C19, you dapat long chain hydrocarbon. So this long chain hydrocarbon have high energy content untuk you move you punya lori lah. So of course dia punya chain of you punya composition feedstock tu memainkan peranan untuk energy content you punya minyak. Itu sahaja.
Okay. Is it clear?
Okay, thank you for the answer.
Okay.
Okay, thank you, Dr. Nurul. Then another question? Yeah, please.
Moderator, I have question.
Oh, we also have questions from online participants. Maybe we're gonna go to online participant first.
Yeah, please mention your question, your name and your question.
Hello, is it me?
Yeah.
Yeah.
Yeah, you are audible now.
I'm Hasliza from UBD. Dr. Ashikin, I find it quite interesting that you also test your biojet fuel, blended them with the fuel for aviation fuel, and then how did you test the performance? Did you put it in the real jet engine?
No.
Yeah.
Unfortunately, we have in Malaysia, we have diesel engine. That's why we can test the CO2, SOx, NOx emission, that one. But unfortunately, we don't have the flight engine here in Malaysia. And then if we have, we need to have a lot of oil.
Yeah.
But we studied the simple like soot testing, this kind of viscosity testing, flash point. So we able to at least get information, basic information about what is the impact of our fuel in the engine. But like proper engine, not like diesel engine. We don't have that accommodation.
Okay, thank you.
Alright.
Okay, thank you so much, Dr. Hasliza, for the question. All right, and now we move to the next question from participants in this room. Yeah, please mention your name and your question.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam.
Let me introduce myself. My name is Marcella Audiatati. I want to ask, what is the role of catalytic technology in the biomass waste conversion process to biofuel, and how can the concept of catalysis enhance production efficiency? Thank you.
Okay, yeah, the role of catalytic and how can the concept of catalytic enhance?
I admit that I'm not emphasizing on the catalyst because I just want to show you guys the product already successful produced from my project. Yes, we need to have a look at the definition of the catalyst itself. Catalyst is needed in order for us to promote our reaction. So the catalyst is very important for us to speed up the reaction. Okay, so without the catalyst, we cannot reduce the activation energy, and then we cannot speed up the reaction. So yes, catalyst is very important in order for us to promote all of the reaction: deoxygenation reaction, hydrodeoxygenation reaction, transesterification reaction. The first question about the role of catalyst. Every catalyst have different capability. Like Dr. Hasliza used the catalyst for converting cahaya water splitting in order to produce hydrogen. Mine, I'm using my catalyst, for example, like calcium oxide, in order to transesterify the soybean oil into biodiesel. In order to transesterify this process, we need to have catalyst which is not sensitive with high FFA. So we need to have basic catalyst. But if you use acid catalyst, it will not workable. So setiap reaction dia mempunyai catalyst berbeza-beza. Tak semua catalyst dia work untuk satu reaction, dan tak semua catalyst work dekat reaction ni, dia tak work dekat reaction ni. So dia possibly dia akan work tapi selectivity. Contohnya, saya nak produce minyak kapal terbang SAF, and then saya nak produce minyak lori iaitu diesel. Mungkin saya boleh menggunakan catalyst yang sama, tapi saya bezakan dia punya minyak sahaja. Dia akan work. Tapi catalyst sangat pentinglah untuk promote the reaction. Untuk produk minyak gasoline, kerosin dengan SAF ni, catalyst ni tak berapa penting sangat sebenarnya. Kalau you nak produce minyak kapal terbang, you kena pastikan that you punya feedstock tu, feedstock fatty acid dia adalah pendek. Kalau you nak buat minyak lori, pastikan feedstock you, fatty acid chain dia panjang. Catalyst apa-apa pun you dapat produce, tapi cuma selectivity dia mungkin rendah atau tinggi. Itu sahaja.
Okay, thank you, Dr. Nurul, for explaining more about catalyst. Yeah, I think that is clear enough. Then, other question? No other question from offline participants. How about online participants? Okay, I think that's all the questions for you, Dr. Nurul. Yeah,
Thank you.
Yeah, thank you so much for all of the explanation and the response for the questions. I hope that you get well very soon. We can meet in another conference or opportunities. All
Okay,
right.
okay, thank you.
Yeah, thank you so much. All right, ladies and gentlemen, I think Dr. Nurul and Dr. Hasliza have finished the explanation or their keynote speech, and it means that it's the end of my session. So we have engaged in insightful discussions. Then both of the speakers already explained the very important topic for today. Then I really thanks for the keynote speakers, and also I really appreciate all of the participants who have participated actively in this session. Yeah, then let's give applause for our keynote speaker first. Yeah. Yang online bisa kasih online applause juga ya. Okay, thank you. All right. I think that's all for me. Thank you for joining with me in this session. Last, I say Assalamualaikum warahmatullahi wabarakatuh. Then we will continue to the next session after the break, right? Yeah, after the break. So make sure that all of you are stay here or stay in our YouTube channel. Yeah. Thank you.